Hello, friend. Welcome back. Or if this is your first time here, welcome home. Some nights the universe feels closer than it should. Stars pulse in rhythms we can't hear. Time stretches in ways clocks cannot measure. And somewhere out beyond the edge of what we know, strange things are happening. Things that shouldn't exist. Things that break the rules we thought were absolute. Tonight we're going to drift through the strangest phenomena ever observed in the universe. Not the loudest, not the brightest, but the quietest mysteries. The ones that make scientists pause mid-sentence. The ones that rewrite textbooks in whispers. Before we begin, if you find comfort in these quiet journeys through the cosmos, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell. Not for noise, but so the next quiet night can find you again. These small gestures help this channel reach others who need the night sky explained in whispers. Now, let's drift. The universe is stranger than we imagine, perhaps stranger than we can imagine. And the beautiful thing, we don't need to solve every mystery tonight. We just need to feel the wonder of not knowing, to rest in the questions. Consider this. Right now, as you listen, light from distant galaxies is bending around massive objects in space, arriving at Earth from paths it shouldn't take. Dead stars are spinning hundreds of times per second, keeping time more accurately than any clock humanity has ever built. And somewhere in the cosmic dark, there are voids so empty, so impossibly vast, that they challenge everything we thought we understood about how the universe began. These aren't science fiction. These are observed facts, real phenomena documented by real telescopes, measured by real instruments, studied by real people who dedicated their lives to understanding what shouldn't be possible. The ancient Greeks looked up and saw gods. The medieval scholars looked up and saw divine machinery. We look up and see something perhaps even stranger. A universe that follows laws. Yes, but laws so bizarre, so counterintuitive that they feel like poetry written in mathematics. You know what's remarkable? Every strange thing we'll explore tonight was once invisible, not because we lack the technology to see it, though that's partly true, but because we lack the imagination to even ask the right questions. Who thinks to ask, can light travel in curves? Who thinks to wonder, can a star exist inside another star? Who dreams up the possibility of rain made of glass, falling sideways at thousands of miles per hour on planets so far away? We'll never touch them. Scientists do. Not because they're smarter than the rest of us, but because they're more comfortable with being wrong. They ask impossible questions, and then quietly, patiently, they wait for the universe to answer. And sometimes the universe answers in ways that make the question seem small. Think about gravity for a moment. We live with it every day. It pulls us down, keeps our coffee in our cups, makes dropped things fall. Simple, right? Intuitive. You don't need equations to understand that things fall. But gravity isn't what you think it is. It's not a force pulling you down. It's the shape of space itself, curved by the presence of mass. You're not being pulled to Earth. You're following the straightest possible path through curved space-time. Standing still right now, you're actually accelerating upward through space-time, and the ground beneath you is preventing you from following your natural trajectory. Does that make sense? Not really, not to our everyday minds, but it's true. Provably, measurably true. And if space can curve, if the very fabric of reality can bend like a trampoline under a bowling ball, then what else is possible? In 1915, Albert Einstein published his general theory of relativity. The math was beautiful, elegant even, but the predictions seemed absurd. Light should bend around massive objects. Time should slow down near heavy things. The universe itself should be either expanding or contracting, unable to sit still. Other physicists read his work and thought interesting mathematics probably not real. And then, in 1919, during a total solar eclipse, astronomer Arthur Eddington measured starlight passing close to the sun. The stars appeared slightly out of position. Their light had bent just as Einstein predicted. Space itself had curved. That moment changed everything. Not just physics, but our entire understanding of what reality is. Because if light can bend, if the straightest path isn't straight, then we live in a universe far stranger than our senses tell us. Here's something that might help you sleep tonight, or keep you awake. Light from distant stars doesn't travel in straight lines to reach us. It follows the curves of space-time, winding through gravitational wells, skating along the edges of massive objects, arriving at our telescopes from angles that shouldn't exist. Every photon is a tiny time traveler carrying information across billions of years, and some of them take the scenic route. Scientists discovered something even stranger. When a very massive object sits directly between Earth and a more distant light source, the light doesn't just bend once. It bends around all sides of the massive object, creating multiple images of the same distant source. Imagine looking at a candle through a wine glass. The glass warps the light, and you might see two candles, or three, or a ring of light. That's happening on cosmic scales. In 1985, astronomers discovered something now called the Einstein cross, 4 bright spots arranged in a perfect cross pattern around a dimmer galaxy. But here's the thing, those 4 spots aren't 4 different objects. They're 4 images of the same quasar, a bright object billions of light years away. The massive galaxy in the middle is bending the quasar's light around it like a cosmic lens. 4 images, 1 source. Light bent by gravity. But it gets stranger. Remember, light takes time to travel. So these 4 images aren't just bent in space, they are also separated in time. The light creating each image took a slightly different path, a different distance to reach Earth, which means each image shows the quasar at a slightly different moment in its history. You're seeing the same object at 4 different times simultaneously, past and present existing together in a single photograph. The universe doesn't just bend space, it bends time. It tangles them together into something Einstein called spacetime. And massive objects create ripples, curves, and folds in this fabric that light must follow. Does this make you feel small? It should, but also somehow connected, because the light entering your eyes right now reflected from this screen, or this room, is following the same rules, curved by Earth's gravity however slightly, bent by the sun's mass as it travels from screen to eye. You are part of this strange geometry. We all are. Let me tell you about gravitational lensing a different way. Imagine the universe as a vast, dark ocean. Light travels through it like ripples on water. Now, imagine dropping massive stones into this ocean star's galaxies, clusters of galaxies. Each creates a depression, a curve in the fabric of space. When light ripples past these depressions, it doesn't go around them. It follows the curve down and back up, like a marble rolling through a bowl. The path is longer, more curved, but to the light, it's still the straightest possible route. This isn't metaphor. This is physics described poetically. Astronomers use this phenomenon now. They search for these gravitational lenses, these cosmic magnifying glasses, because they reveal things we couldn't otherwise see. Distant galaxies too faint to detect become visible when a massive galaxy cluster sits between us and them, focusing the light, brightening it, making the invisible visible. The universe has given us a tool. Mass bends light. Gravity is a lens. And by studying how light bends, we can map the invisible mass in space. The dark matter we cannot see directly but know must exist because of how it curves the light around it. Strangeness becomes utility. Mystery becomes method. Have you ever wondered if what you see is what's really there? Gravitational lensing suggests the answer is no. Light takes the path of least resistance through curved space, and that path isn't always direct. What appears to be in one location might actually be somewhere else entirely. Position becomes relative. Distance becomes negotiable. In the year 2003, astronomers discovered a phenomenon they named the cosmic horseshoe, a nearly perfect ring of light, bright and blue, wrapped around a massive red galaxy. That ring isn't a ring at all. It's a single distant galaxy stretched and smeared by the gravity of the foreground galaxy into a shape that looks like a horseshoe. One galaxy bent into a circle, curved so severely that it almost meets itself. Light, remembering the weight of giants. Think about what this means for our understanding of sight itself. We trust our eyes. We believe that seeing is knowing. But gravitational lensing teaches us that light is a traveler with a story. It bends it, delays it, splits into copies of itself. What we see is not what exists, but what existed filtered through the gravitational landscape of everything between there and here. Every observation is an interpretation, every image a reconstruction. The universe doesn't lie, but it doesn't tell the whole truth either. Scientists estimate that we can see farther into space using gravitational lenses than we ever could with telescopes alone. Some of the most distant galaxies ever observed are only visible because a massive cluster of galaxies sits between us and them, magnifying their light by factors of 10, 20, even 50. We are seeing across time and space by reading the curves that gravity writes into light. And here's a thought to carry into sleep. This bending happens everywhere. Every star curves the space around it. Every planet, every moon, even you. Your mass, small as it is, creates a tiny dimple in space-time. Light passing near you bends imperceptibly following the curve you create just by existing. You are part of the geometry of the universe. You bend light. You curve space. You matter literally in the physics sense of the word. Strangeness isn't out there in distant galaxies. Strangeness is here now, woven into the fabric of everything. When Einstein first proposed that gravity could bend light, he doubted we'd ever see it happen. The effect is so small, so delicate that measuring it seemed impossible with the technology of his time. He published the idea almost as a curiosity, a mathematical consequence of his equations, not expecting it to be tested. But Eddington believed. He organized expeditions to 2 locations where a total solar eclipse would occur in 1919, one in Brazil, one on an island off the coast of West Africa. During totality, when the sun's light was blocked, stars near the sun became visible. Eddington photographed them and compared their positions to where they appeared when the sun wasn't nearby. The stars had moved. Not much, just one. 75 arc seconds, the width of a quarter, seen from 2 miles away. But they had moved exactly as Einstein predicted. Light bends, space curves, and we could measure it. That measurement made Einstein famous overnight. Newspapers around the world announced that Newton had been overthrown, that space and time were not what we thought. People who couldn't understand the mathematics felt the strangeness of it anyway. The universe had revealed itself to be weirder than common sense suggested. And that's the thing about strangeness. It doesn't announce itself with fanfare. It hides in small discrepancies and measurements that don't quite match expectations in photographs, where stars appear slightly out of place. Strangeness is patient. It waits for us to look closely enough. Now, as you rest here in the quiet, consider this: the light reaching Earth tonight from distant galaxies left those galaxies billions of years ago. It has traveled through expanding space past gravitational wells around galaxy clusters, through clouds of gas and dust, bent and delayed, and sometimes split into multiple paths. And all of it arrives here now in this moment, carrying information about a universe that existed long before humans looked up and wondered. We are receivers of ancient light, collectors of bent photons, students of a cosmos that teaches through strangeness. Some nights, the universe feels wider than it should. Stars breathe slower. Time folds in silence. And maybe that's because we're finally learning to see what was always there. Not with our eyes alone, but with instruments that measure the invisible, with mathematics that describes the impossible, with minds willing to accept that reality is far stranger, far more beautiful than we were taught. Light bends, space curves, time dilates. And even in our confusion, even in our not quite understanding, there is wonder. You don't need to grasp it all. Just let it drift through your thoughts. Let strangeness become familiar, one whisper at a time. But light bending around gravity is just the beginning. Because if dead stars can bend space, imagine what they do to time itself. Imagine what happens when a star collapses so completely that it becomes a cosmic timekeeper, spinning faster than anything in the known universe, more precise than any clock humanity has ever built. That's where we're drifting next, into the strange music of dead stars, into rhythms that shouldn't exist, into the heartbeat of pulsars that mark time for a universe that barely notices. Imagine standing in a forest where every tree bends light instead of blocking it, where looking through the branches doesn't obscure your view but multiplies it, showing you the same distant mountain from 4 different angles at once. That forest exists, not on Earth, but woven into the fabric of space itself. In 1936, Albert Einstein received a letter from an amateur scientist suggesting that gravity could act like a lens bending light from distant stars in useful ways. Einstein was skeptical. He calculated the mathematics and concluded yes, theoretically possible, but the effect would be so tiny, so impossibly difficult to observe that it held no practical value. He published a paper essentially dismissing the idea. He was wrong. Beautifully productively wrong, because 50 years later, astronomers discovered something that would have astonished even Einstein: a perfect cosmic accident, a alignment so precise it seemed designed for our benefit. In 1985, a team of astronomers pointed their telescope toward a region of space in the constellation Pegasus. They were studying quasars, those impossibly bright objects powered by supermassive black holes billions of light years away. But what they found wasn't one quasar. It was 4 bright points of light arranged in a perfect cross pattern surrounding a faint galaxy. At first, they thought 4 separate quasars coincidentally aligned, but the spectroscopy told a different story. The light signatures were identical, same brightness fluctuations, same chemical composition, same distance from Earth. 4 images, 1 object. Light bent by gravity into a cross. They named it the Einstein cross, and it became the most famous example of strong gravitational lensing ever observed. Here's what's happening. The quasar sits about 8 billion light years away from Earth. Between us and that quasar, about 400 million light years closer, sits a massive galaxy named ZW 2237 plus 030. This galaxy is so massive, so gravitationally powerful, that it warps the space around it like a heavy ball sitting on a stretched rubber sheet. When light from the distant quasar travels toward Earth, it encounters this warped space, and space being curved offers not one path, but many. Light takes all available paths, simultaneously flowing around the galaxy from multiple directions converging at Earth from 4 separate angles. We see 4 quasars. The universe sees one source, 4 paths. Think about what this means for our perception of location. Where is the quasar really? If we look up and see 4 bright spots, which one represents the true position? The answer is none of them, and all of them. Position becomes a story that gravity tells light and light tells us. But here's where it gets even stranger. Light is fast, but it's not instantaneous. It travels at 186,000 miles per second. And even at that speed, crossing billions of light years takes billions of years. Each of the 4 paths the light takes around the lensing galaxy is a slightly different length. One path might be a few hundred light years longer than another, which means the light traveling that path takes a few hundred years longer to reach us. So, when we photograph the Einstein cross, we're not just seeing 4 spatial images of the same quasar. We're seeing 4 temporal images, 4 different moments in the quasar's history, separated by decades or centuries, displayed simultaneously in a single photograph, past and present existing together. In 1990, astronomers observed a brightening event in one of the 4 images of the Einstein cross. The quasar had flared, releasing extra energy. They predicted that the same flare would appear in the other three images at calculable delays based on the different path lengths the light would travel, and it did. Like clockwork. Like the universe itself was conducting an experiment for our benefit, showing us that time is not universal, that one depends on where you are and which path you take. The delays were measured in days and weeks. Image A brightened. 20 days later, image B brightened. Then, image C. Then, image D. The same event rippling through time, arriving at Earth in installments. Gravitational lensing doesn't just bend space. It shuffles time like a deck of cards dealing moments out of order, letting us witness cosmic history non-sequentially. Does this seem impossible? It should. But impossibility is just unfamiliarity wearing a mask. Let me tell you about another lens stranger still. In 2003, astronomers discovered what they now call the cosmic horseshoe. A nearly perfect ring of blue light, bright and symmetrical, wrapped around a massive red galaxy like a halo. That ring isn't a ring. It's a single galaxy stretched and smeared by gravitational lensing into a shape that almost closes on itself. The distant galaxy sits almost directly behind the foreground galaxy, and its light bends around all sides, creating this horseshoe of stretched starlight. Imagine taking a photograph of someone and pulling the edges until their face wraps around a ball. That's what gravity does to light. And yet, despite the distortion, despite the warping, astronomers can reverse engineer the process. They can unwrap that horseshoe, mathematically reconstruct what the original galaxy looks like, measure its distance, study its composition. Distortion becomes information. Warping becomes a tool. Gravitational lensing has revealed galaxies that existed when the universe was less than 1 billion years old, too faint, too distant to see directly, but brightened and magnified by the cosmic lenses between them and us. They become visible. The universe has given us magnifying glasses. All we had to do was learn to recognize them. There's a phenomenon called Einstein rings. When the alignment is perfect, when a massive object sits exactly between Earth and a distant source, the light doesn't form multiple images or horseshoes. It forms a complete ring, a circle of light perfectly symmetrical surrounding the lensing object. These rings are rare. They require precision alignment across billions of light years. But they exist. Astronomers have cataloged dozens of them. Each one is a reminder that the universe operates on scales where coincidence and design become indistinguishable, where the improbable happens routinely, where beauty emerges from mathematics. Here's something that might help you drift into sleep or keep you awake in wonder. The Hubble Space Telescope has discovered gravitational lenses that create not 4 images, not rings, but dozens of images of the same distant galaxy scattered across the sky like jewels on a necklace. Massive galaxy clusters containing hundreds of galaxies create gravitational fields so complex, so deeply curved, that light from objects behind them fractures into dozens of paths. Each path creates an image. Each image a ghost of the original, bent through a different fold in space-time. Looking at these clusters is like looking through a kaleidoscope made of gravity. One galaxy becomes many. Time becomes negotiable. Space becomes fluid. Scientists use gravitational lensing to map dark matter. You've heard of dark matter, perhaps. The invisible substance that makes up most of the mass in the universe but doesn't emit light, doesn't interact with electromagnetic radiation, can't be seen directly. How do we know it exists? Because we can see its gravity bending light. When astronomers study how light bends around galaxy clusters, they measure the mass required to create that bending. Then they count the visible matter. Stars, gas, dust. The numbers don't match. There's far more gravity than visible matter can account for. Something invisible is there curving space-bending light. We can't see it, but we can see what it does. Like wind-bending grass, invisible but undeniable. Gravitational lensing makes the invisible visible, not directly, but through inference, through shadows, through the way light remembers being bent by something we cannot see. In 2012, astronomers discovered a galaxy cluster so massive, so gravitationally powerful, that it acts as the strongest gravitational lens known. They named it MAX J0717. This cluster contains the mass of 3,000 trillion suns, compressed into a region of space a few million light years across. Looking through MAX J0717 is like looking through the most powerful telescope ever built. Galaxies behind it appear magnified by factors of 50 or more. Galaxies that would be invisible become bright enough to study in detail. The cluster isn't trying to help us. It's just existing warping space by being massive. But the effect is the same. The universe has given us a tool, and we've learned to use it. Think about that for a moment. We live in a cosmos where mass bends space, where space curves light, where light carries information across billions of years, and where by pure accident of alignment, some massive objects magnify distant objects for our benefit. We could live in a simpler universe, a universe where light travels straight, where mass doesn't curve space, where seeing is simple. But we don't. We live here in this strange, curved-lensed reality where observation requires interpretation, where position is relative, where time is flexible. And somehow that's more beautiful. There's a type of gravitational lens called a microlensing event. It happens when a smaller object, maybe a planet or a rogue star, passes between Earth and a distant star. For a brief time, days or weeks, the foreground object's gravity focuses the background star's light, making it appear brighter. Then, the alignment ends, and the star returns to its normal brightness. Astronomers use this to discover planets around distant stars. They can't see the planet directly. But when it passes in front of a background star, its gravity creates a brief brightening, a spike in light that reveals the planet's presence. Invisible things detected by the way they bend light. Absence proven by its effects. In 1919, when Arthur Eddington measured starlight bending around the sun during a solar eclipse, he was testing a prediction from Einstein's general relativity. The measurement was difficult, the margin of error large, but the result was clear enough light bends. That single observation changed physics. It validated Einstein's radical idea that gravity isn't a force, but a curvature of space-time. It showed that light, despite having no mass, still responds to gravity by following the curves in space. And it opened the door to everything we've discovered since. Gravitational lensing, gravitational waves, black holes, the expansion of the universe. All of it flows from that one strange truth. Mass curves space, and light follows the curves. Sometimes I wonder what Einstein would think if he could see the Einstein cross. The phenomenon he dismissed as impractical, as too small to matter, now one of the most studied objects in astronomy, a teaching tool, a laboratory for testing physics at cosmic scales. He'd probably smile. Scientists love being wrong if it means reality is more interesting than they thought. Here's a question you can carry into the quiet: if light can bend, if paths can curve, if the straightest route through space is actually a winding journey through gravitational wells, then what does straight even mean? In our everyday lives, we think of straight lines as the shortest distance between 2 points. But in curved space-time, straight lines don't exist. Every path is curved by the presence of mass. The line you draw on paper curves through three-dimensional space because Earth's gravity pulls on you, and the paper and the pencil. Nothing is straight. Everything bends. Straightness is an approximation useful, but not true. Does that bother you? It shouldn't. It's freeing in a way. If even light doesn't travel in straight lines, if even paths through empty space are curved by invisible mass, then maybe the winding journey is the only kind of journey there is. Maybe arrival matters less than the route. Maybe the bending is the point. Gravitational lensing has shown us galaxies that formed when the universe was only a few 100 million years old. Young galaxies bright and blue with the light of massive stars, magnified by the cosmic lenses between them and us. Without those lenses, we couldn't see these galaxies. They're too far too faint. but magnified 50-fold, 100-fold, they become visible, knowable, studable. The universe is teaching us to see farther by using the tools it provides: mass as a lens, gravity as a magnifier, space-time as a medium that doesn't just transmit light but shapes it, guides it, delivers it to us from impossible distances. We are receivers, interpreters, students of a cosmos that doesn't simplify itself for our convenience but rewards those patient enough to learn its language. Light bends, time delays, images multiply, and in the multiplication and the delay and the bending, we find information we couldn't access any other way. Strangeness again becoming utility. As you rest here, let this thought drift through every photon that reaches your eye has traveled some distance through curved space. Even light from the lamp beside you curves slightly in Earth's gravitational field. Even light from the screen in front of you follows a path bent by the mass of the planet beneath you. You live in curved space. You always have. You just didn't notice because the curvature is so gentle, so consistent, that it feels like flatness. But it's not. Space is curved everywhere mass exists. And mass exists everywhere. So space is always curved, always bending, always guiding light along paths that aren't straight but feel inevitable. The universe doesn't give us straight lines. It gives us geodesics, the curved paths that light follows through the geometry of space-time. And those paths, winding and bent as they are, carry the history of the cosmos to anyone willing to look up and wonder. Light remembers being bent. Light carries the story of every gravitational well it passed through. And when that light reaches us, enters our telescopes, our instruments, our eyes, it tells us about the universe, not as it appears, but as it truly is, curved, dense, strange, and beautiful. But if gravity can bend light, imagine what it does when concentrated into something far denser than a galaxy. Imagine a star that collapses so completely that a piece of it the size of a sugar cube weighs as much as a mountain. Imagine that object spinning hundreds of times per second, sweeping beams of radiation through space like a cosmic lighthouse. Imagine that these objects keep time more precisely than any clock humanity has ever built, and that we discovered them by accident, thinking for a moment we might have found a signal from another civilization. That's the strange music of dead stars, and that's where we're drifting next. There's a sound the universe makes that you can't hear, a rhythm so precise, so mathematically perfect, that when humans first detected it, we thought we'd found proof of alien intelligence. Beep, beep, beep. Regular as a heartbeat, faster than thought. A pulse from the corpse of a star. It was July 1967. A graduate student named Jocelyn Bell was analyzing radio telescope data at Cambridge University. Her job was to search for quasars, those distant bright objects we talked about earlier. But she kept finding something else, something strange, a signal that repeated every 1.3373 seconds, precise to within a millionth of a second. At first she thought it was interference, radio signals from Earth, maybe a satellite, maybe equipment malfunction. But the signal appeared at the same spot in the sky every night, rising and setting with the stars. It was coming from space. Something out there was broadcasting a regular pulse, and nothing natural should do that. Her supervisor, Anthony Hewish, jokingly called it LGM1, Little Green Men Number 1. They weren't serious about aliens, not quite. But the regularity was unsettling. What natural phenomenon keeps time that precisely? The answer, it turned out, was death. What Jocelyn Bell had discovered was a pulsar, not a signal from intelligent life, but something perhaps even stranger. The collapsed core of a massive star spinning hundreds of times per second, sweeping beams of radiation through space like a lighthouse. Every time the beam swept past Earth, the radio telescope registered a pulse. The universe had lighthouses, and they were made from stellar corpses. Let me explain what a pulsar actually is, because the physics is beautiful and strange. When a massive star runs out of fuel, it collapses. The outer layers explode in a supernova, but the core implodes, crushed by its own gravity, until protons and electrons merge into neutrons. What remains is a neutron star. Imagine taking the mass of the sun and compressing it into a sphere about 12 miles across. The density is incomprehensible. A teaspoon of neutron star material would weigh about 1 billion tons. The gravity at the surface is 200 billion times stronger than Earth's. And because of a principle called conservation of angular momentum, when the star collapses, it spins faster, much faster, like a figure skater pulling in their arms during a spin. Some neutron stars rotate 700 times per second. 700 complete rotations in the time it takes you to say the word rotation. And as they spin, they emit beams of radiation from their magnetic poles. If those beams happen to sweep across Earth, we detect pulses. Regular, precise, relentless. The universe keeps time with dead stars. After Jocelyn Bell's discovery, astronomers found more pulsars. Dozens, then hundreds, then thousands. Each one a collapsed star, each one spinning at a different rate, each one keeping perfect time across billions of years. And here's what astonished physicists: pulsars are more accurate than atomic clocks. The best atomic clocks humanity has built measure time to within 1 billionth of a second per day. They're the most precise instruments we've ever created. But some pulsars are more stable. Their pulses arrive with such regularity that over the course of years they deviate by less than a microsecond. Dead stars keeping better time than our best technology. Scientists now use pulsars as cosmic clocks. They're called pulsar timing arrays, networks of radio telescopes that monitor dozens of pulsars, simultaneously measuring the arrival times of their pulses with nanosecond precision. Why? Because those pulses travel through space and space itself can ripple. Gravitational waves distortions in the fabric of spacetime, caused by massive objects in motion, stretch and compress space as they pass through. When a gravitational wave passes between a pulsar and Earth, it changes the distance the pulses travel ever so slightly. By monitoring many pulsars and looking for correlated timing, scientists can detect gravitational waves that are otherwise too faint to measure. The pulsars become detectors. Their dead spinning regularity turns them into instruments for measuring ripples in reality itself. Strangeness once again becoming utility. Corpses becoming tools. Let me tell you about the fastest pulsar ever discovered. It's called PSRJ 1748-2446 AD, and it rotates 716 times per second. 716 complete rotations every single second. The surface of this star is moving at roughly 24% the speed of light. Think about that. A ball of neutrons 12 miles across, spinning so fast that its equator approaches 1/4 of light speed. Matter at that speed experiences relativistic effects. Time dilates, space contracts. The star is nearly tearing itself apart, held together only by gravity so intense it warps space-time around it. And yet, the pulses arrive at Earth with clockwork precision. Beep, 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 716 times per second, year after year after year. How long can a pulsar keep spinning? The answer depends on how it loses energy. Pulsars emit radiation, and radiation carries energy away. Slowly, over millions of years, they spin down. The pulses arrive slightly less frequently. The lighthouse beam slows. But the slowdown is gradual, predictable, measurable. Some pulsars have been monitored for decades, and their spin-down rate matches theoretical predictions to extraordinary precision. The universe is consistent. Even in Death stars follow rules. In 2003, astronomers discovered something unprecedented: 2 pulsars orbiting each other. They named it the double pulsar, PSRJ 0737-3039, 2 neutron stars, each about 12 miles across, each spinning dozens of times per second, orbiting their common center of mass once every 2.4 hours. Imagine two stellar corpses, each more massive than the Sun, each spinning like cosmic tops, locked in a gravitational dance so tight they circle each other faster than Earth rotates. The system is a physics laboratory. By measuring the pulses from both pulsars, astronomers can test Einstein's general relativity with unprecedented precision. The orbit changes slightly over time, exactly as relativity predicts. The pulsars are emitting gravitational waves, losing energy spiraling closer together. In about 85 million years, they'll merge. The collision will release a burst of gravitational waves so powerful it will ripple across the entire universe. And somewhere, if anyone is listening, they'll detect the signal, the final scream of two dead stars becoming one. But for now, they just pulse, regular, precise, teaching us about gravity by dancing toward oblivion. Here's something strange about pulsars that bothers physicists in the best way. When a pulsar first forms right after the supernova, it should be spinning fast. We expect that. But some young pulsars spin slowly, much slower than they should. Why? The answer seems to be magnetic fields. Neutron stars have magnetic fields trillions of times stronger than Earth's. These fields interact with surrounding material, with the stellar wind, with charged particles in space. The interaction creates drag, slowing the pulsar down. But the exact mechanism isn't fully understood. We know it happens. We can measure it. But the details remain mysterious. Even in things we've studied for 50 years, strangeness persists. There's a type of pulsar called a millisecond pulsar. These spin hundreds of times per second, far faster than ordinary pulsars. And they're old. Very old. Some are billions of years old, which doesn't make sense. Old pulsars should have spun down by now. The explanation involves something called spin-up. These pulsars aren't alone. They orbit companion stars, and over millions of years, they siphon material from those companions. The infalling matter carries angular momentum, transferring it to the pulsar, spinning it back up. It's called recycling. A dead star brought back to rapid rotation by cannibalizing a companion. The universe wastes nothing. Even death serves a purpose. Millisecond pulsars are the most stable clocks in the known universe. Their pulses arrive with such regularity that astronomers use them to test fundamental physics. Is the speed of light truly constant? Do the laws of physics change over time? Are we moving through gravitational waves we haven't detected yet? The pulsars provide answers, not by speaking, but by keeping perfect time year after year, allowing us to measure the universe against their unwavering rhythm. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a pulsar orbiting a companion star. They measured the orbit, carefully tracking how the pulsar's position changed over months and years. And they noticed something strange. The orbit was shrinking. The pulsar and its companion were spiraling closer together, losing about 75 millionths of a second per year. Where was the energy going? Einstein's theory predicted gravitational waves. Two massive objects orbiting each other should emit ripples in spacetime, and those ripples should carry energy away, causing the orbit to decay. Hulse and Taylor measured the orbital decay rate and compared it to Einstein's predictions. The match was perfect. This was the first indirect evidence that gravitational waves exist. They won the Nobel Prize for it. The pulsars had proven Einstein right decades before we could detect gravitational waves directly. Sometimes I think about Jocelyn Bell, a graduate student analyzing radio data, finding a signal that shouldn't exist. She could have ignored it, dismissed it as noise, but she didn't. She investigated. She asked questions. She told her supervisor. And because of her curiosity, because she didn't look away from the strange signal, we discovered a new class of objects. We learned that neutron stars exist. We found cosmic clocks. We tested general relativity. We detected gravitational waves indirectly. All because someone noticed something that didn't fit. Science is often portrayed as grand theories and brilliant insights, but sometimes it's simpler. Sometimes it's just noticing what doesn't belong and being curious enough to ask why. By the way, Jocelyn Bell didn't win the Nobel Prize for discovering pulsars. Her supervisor did. She was excluded from the award, a decision many physicists now consider unjust. But she continued her career, made other discoveries, and has been recognized since with numerous other awards and honors. She changed astronomy, and the universe keeps pulsing indifferent to human awards, broadcasting its strange music to anyone willing to listen. Here's a question you can carry into the quiet. What does it mean for a dead thing to keep time? We think of clocks as human inventions tools we build to measure something abstract, but Pulsar suggests that timekeeping is natural, that regularity exists in the cosmos, without observers, without purpose, simply as a consequence of physics. A neutron star doesn't know it's keeping time. It's just spinning. The pulses are just radiation sweeping through empty space, but we perceive them as beats, as rhythm, as a cosmic metronome marking seconds across the galaxy. Does the universe have a heartbeat? Maybe. Maybe it has billions of them scattered across space, each one a collapsed star pulsing in the dark. There are over 3,000 known pulsars now, each one unique, each one spinning at its own rate, located at its own distance, emitting its own particular frequency of radiation. Astronomers catalog them, map them, monitor them. Listen to their pulses like distant drums, learning what we can from their unwavering rhythm. And occasionally, we discover a new one. A signal appears in the data, regular and strange, and we realize the universe has revealed another lighthouse, another clock, another dead star refusing to be silent. Some pulsars emit pulses in the visible light spectrum. You can see them blink if you have a sensitive enough telescope. Others emit X-rays, gamma rays, radio waves across multiple frequencies simultaneously. They're not trying to communicate. They're not lighthouses built for travelers. They're just physics spinning and radiating, doing what collapsed stars do. But from our perspective, millions or billions of light years away, they look like beacons, like signals, like messages sent across the void saying, "Here's something strange exists, and it keeps perfect time." The pulses from a typical pulsar cross the galaxy in tens of thousands of years, traveling through dust and gas and magnetic fields, bending slightly around massive objects, arriving at Earth, carrying information about everything they pass through. By studying how the pulses change, astronomers learn about the interstellar medium, the space between stars. Tiny delays in pulse arrival times reveal clouds of ionized gas. Variations in pulse shape indicate magnetic fields. The pulsars become probes. Their regularity highlights anything that disrupts it, anything that changes the journey the pulses take. Silence in the universe is rare. But between the pulses, there's a kind of quiet, a gap where the beam sweeps past us, pointed elsewhere, illuminating some other part of the cosmos we'll never see. The pulsar doesn't care. It just spins, radiates, keeps time for a universe that doesn't ask. And we listen, we measure, we wonder what it means that dead stars are more reliable than our best clocks, more regular than our own heartbeats, more persistent than anything alive. Maybe there's comfort in that. The idea that even after everything ends, even after stars exhaust their fuel and collapse and die, something remains. A spin, a pulse, a rhythm that echoes across billions of years. Death, it seems, has its own kind of life, its own persistence, its own strange music. As you drift here in the quiet, think about those pulsars. Scattered across the galaxy, spinning in darkness, broadcasting pulses no one might ever hear. Most of them pulse in empty space, their beams sweeping across voids where no planets orbit, no telescopes listen. But they pulse anyway, regular, precise, indifferent. The universe doesn't perform for an audience. It just exists strange and beautiful whether we're watching or not. And speaking of strange existence, imagine a place in the universe so empty that it challenges our understanding of how matter should be distributed. Imagine voids hundreds of millions of light years across, containing almost nothing. No galaxies, no stars, no light. Just emptiness on a scale that shouldn't exist according to our models of cosmic structure. These voids are real, and they're stranger than the spaces between stars. That's where we're turning next, into the great cosmic emptiness that refuses to make sense. What's stranger than something that shouldn't exist? Nothing that shouldn't exist. Emptiness carved into the fabric of everything. Voids so vast, so impossibly hollow, that they challenge our understanding of how the universe formed. Places where galaxies should be, but aren't. Darkness deeper than absence. In 1981, astronomer Robert Kirshner and his team were mapping the distribution of galaxies in space. They expected to find galaxies scattered somewhat evenly, maybe clustered here and there, but generally distributed across the cosmos like stars in the night sky. Instead, they found a hole, an enormous spherical region of space roughly 330 million light-years across, containing almost nothing. A handful of galaxies where there should be thousands. An emptiness so profound it seemed impossible. They called it the Boötes void, but void doesn't quite capture it. This isn't empty space between stars. This is a region where galaxies themselves are missing, where the raw material that should have collapsed into stars and planets and solar systems just didn't. Or did, but somewhere else. The void sits there in the constellation Boötes, a bubble of nothing surrounded by walls of galaxies, and no one fully understands why. Let me give you a sense of scale. The Milky Way galaxy is about 100,000 light-years across. Light takes 100,000 years to travel from one side to the other. The Boötes void is 330 million light-years across. You could fit over 3,000 Milky Ways side by side inside this emptiness and still have room left over. And it's not alone. Astronomers have discovered dozens of supervoids, giant bubbles of near emptiness scattered throughout the observable universe. The universe, it turns out, is less like a smooth soup of galaxies and more like a cosmic foam. Galaxies cluster along filaments and walls, leaving vast voids between them. But even in a foamy universe, the Boötes void is strange. It's too empty, too large, too well-defined. Computer simulations of cosmic evolution struggle to produce voids this extreme. The universe, it seems, can surprise even our most sophisticated models. Here's what we think happened, though. Think is doing a lot of work in that sentence. In the early universe, matter wasn't distributed perfectly evenly. There were slight variations in density, tiny ripples in the distribution of hydrogen and helium. Over billions of years, gravity amplified these ripples. Dense regions attracted more matter, becoming denser. Less dense regions lost matter to their surroundings, becoming voids. The process is called gravitational collapse and expansion. It's how structure forms in the universe. Galaxies cluster together, leaving voids between the clusters. But the Boötes void is more extreme than this process should produce, which means either our models are incomplete or something unusual happened in that region of space. Some fluctuation in the early universe, some quirk of initial conditions that created an unusually large low-density region. We don't know which. We just know the void exists and it shouldn't. Not at that scale. In 1987, astronomers discovered another void in the constellation Eridanus, smaller than Boötes but still immense. And this one came with an added mystery. When scientists mapped the cosmic microwave background, the faint radiation left over from the Big Bang, they found a cold spot, a region where the temperature of the radiation is slightly lower than average, about 70 microkelvins colder, which doesn't sound like much, but in a universe where the background radiation is remarkably uniform, any variation stands out. The cold spot sits in the same direction as the Eridanus void. Coincidence maybe, or maybe related. One hypothesis suggests that as radiation from the Big Bang travels through a supervoid, it loses energy. Photons climbing out of the void's gravitational well stretch to longer wavelengths, becoming cooler. The effect is called the integrated Sachs-Wolf effect, and it could explain why the cold spot exists. But there's a problem. The cold spot is colder than the void should produce. Too cold. Unusually cold. Some scientists have proposed more exotic explanations. Maybe the cold spot is evidence of a collision between our universe and another universe, a place where two cosmic bubbles touch, leaving a mark in the background radiation, a scar from contact with the multiverse. It sounds like science fiction, but the cold spot is real, measured by multiple satellites, confirmed by independent observations, and the standard explanations don't quite fit. So, we're left with a mystery. A cold spot that might be a void or might be something stranger. A temperature anomaly that could be physics we understand or physics we haven't discovered yet. The universe refuses to be simple. Think about what voids mean for structure. If you were an astronomer living in a galaxy inside the Boyde's void, your view of the universe would be profoundly different from ours. You'd look out in every direction and see almost nothing. No nearby galaxies, no rich clusters, just a few scattered islands of light in an ocean of darkness. You might conclude that the universe is sparse, mostly empty, with galaxies being rare exceptions rather than common features. And you'd be wrong. But how would you know your observations would confirm your conclusion? The universe you could see would appear empty because you happen to live in a void. It's a reminder that location matters. Our view of the cosmos is shaped by where we are. We see a universe rich with galaxies because we live in a relatively dense region. But that's not universal, that's local. Truth depends on perspective. Even in physics, the largest void ever discovered is called the Giant Void. It spans about 1 billion light-years across and sits roughly 1 billion light-years away from Earth. 1 billion light-years. Think about that distance. Light has been traveling for 1 billion years, and it's only now reaching us from the far edge of this emptiness. And what's inside? Almost nothing. A few dozen galaxies where there should be tens of thousands. A silence so vast it seems intentional, though of course it's not. The giant void contains about 20% less matter than average regions of space, which doesn't sound dramatic until you realize how much matter that represents. Billions upon billions of galaxies worth of mass missing or redistributed elsewhere. Where did it go? Into the walls surrounding the void, into the filaments and clusters that border the emptiness. Gravity pulled it out over billions of years, leaving the void behind like a cosmic exhale. But here's what bothers cosmologists. The voids are too organized, too spherical, too well-defined. Random processes should create messier structures, irregular shapes, fuzzy boundaries. Instead, we find voids that look almost intentional, almost designed, which they're not. But the regularity suggests underlying physics we might not fully understand. Maybe dark energy plays a role, that mysterious force causing the universe to expand faster over time. In regions where matter density is already low, dark energy might dominate, pushing matter away more effectively, creating these unusually empty voids. Or maybe not. Dark energy is uniform across space, or we think it is. Why would it create voids in some places and not others? We're still figuring it out. Still trying to reconcile observations with theory. There's something poetic about voids, though. The universe is mostly empty space anyway. Between stars, between galaxies, even between atoms, there's vastness. But we notice the matter, the stars, the planets, the light. We map where things are. Voids force us to map where things aren't, to define absence, to study nothing as if it were something. And in doing so, we learn that nothing isn't neutral. Emptiness has structure. Voids have boundaries, histories, effects on the matter around them. Nothing, it turns out, is something after all. In 2015, a team of scientists published research on the cold spot in the cosmic microwave background. They confirmed it's real, not a measurement error. They confirmed it's unusually cold. and they confirmed that the Eridanus supervoid alone can't fully explain the temperature difference. So, what does one possibility is that multiple voids align along our line of sight, stacking their cooling effects. Another is that the void is shaped differently than we think, creating a stronger cooling effect than models predict. Or the more exotic possibility, the cold spot could be evidence of something beyond standard cosmology, a collision with another universe, a topological defect in spacetime, a remnant from the very first moments after the Big Bang. We don't know. The data is real, but the interpretation is open. And that's the beautiful frustration of science. Sometimes we have the answer, and we're searching for the question. Sometimes we have observations that don't fit any answer we've proposed yet. The cold spot is the latter, a fact waiting for an explanation. Here's a thought that might help you drift into sleep or keep you gently awake. Right now, photons from the cosmic microwave background are passing through you. Radiation from the Big Bang, traveling for nearly 14 billion years, arriving at Earth, passing through the atmosphere, through the walls of your room, through your body. Some of those photons pass through voids, stretched by the expansion of space, cooled by climbing out of gravitational wells, marked by their journey through nothingness. You are being touched by light that has experienced absence, that has traveled through the great cosmic voids and carried the story of emptiness across the universe. Does that change how they feel? Numbered light is light, but knowing their history, knowing what they've passed through, makes them more interesting somehow. The universe has about 3 million supervoids that we know of. Most are smaller than Boötes or the giant void, but still immense by any human scale. Each one a bubble of relative emptiness in the cosmic foam. And between the voids, matter clusters. Galaxies form filaments, walls, clusters. The universe self-organizes into a web-like structure with voids as the spaces between the threads. Cosmologists call it the cosmic web. It's the large-scale structure of the universe. And it's beautiful, mathematical, elegant. The natural result of gravity acting on small variations in density over billions of years. But within that elegant structure, there are anomalies, voids too large, spots too cold, patterns that don't quite match predictions. And those anomalies are where discovery happens, where our understanding expands, where the universe teaches us that we don't know everything yet. In the 1960s, before we discovered supervoids, astronomers thought galaxies were distributed more or less randomly across space, scattered evenly with some clustering, but no grand organization. Then we started mapping galaxy positions in 3 dimensions, measuring their distances as well as their positions in the sky. And the structure emerged: walls, filaments, voids. A cosmic architecture far grander than anyone expected. It was a humbling moment. We'd been looking at the universe for centuries and missed the largest structures in it, not because we weren't observant, but because we lacked the tools to see in 3 dimensions at cosmic scales. How much are we still missing? What structures exist at scales we haven't mapped yet? What patterns emerge when you zoom out far enough? We don't know. We're still mapping, still measuring, still discovering that the universe is bigger and stranger than the frame we're using to view it. The Boötes void, by the way, isn't completely empty. It contains about 60 galaxies, 60 in a space that should contain 2,000. Those 60 galaxies are interesting. They formed in a region with less surrounding matter, less gravitational interaction, less merging and colliding than typical galaxies experience. Some scientists study them to understand how galaxies evolve in isolation. What happens when a galaxy doesn't have neighbors? When it's not being pulled and stretched by nearby gravitational fields? Turns out they evolve differently, more slowly, more independently. They're smaller on average, less disturbed. The void in creating absence also creates a unique environment for the few objects that exist within it. Isolation becomes a laboratory. Emptiness becomes informative. Here's a question you can carry into the quiet. If you could travel through a super void, what would you see? At first, probably not much. Space is already mostly empty. The distance between stars in a galaxy is vast. The distance between galaxies in a cluster is vaster. But in a void, the distances would be even greater. You'd travel for millions of years at the speed of light and not encounter a single galaxy. Just darkness, emptiness, the faint glow of the cosmic microwave background, and nothing else. Would it feel lonely? Probably, but also peaceful. No gravitational disturbances, no radiation from nearby stars. Just the slow expansion of space itself, carrying you gently outward along with everything else. A quiet, unlike any quiet on Earth. Some cosmologists have proposed that voids are where dark energy dominates most completely. In regions with little matter, little gravity, dark energy's repulsive effect becomes more apparent. Space expands faster. Matter is pushed away more effectively. If true voids might be glimpses of the universe's future, billions of years from now, dark energy will have pushed galaxies so far apart that most of the universe will look like a void. Islands of light separated by impossible distances, receding from each other faster than light can bridge the gap. Loneliness on a cosmic scale. The heat death of the universe not as a sudden event, but as a gradual separation. Everything drifting apart until even neighboring galaxies are beyond reach. But that's billions of years away. For now, voids are just one feature among many. Strange, yes? Anomalous, perhaps. But part of the cosmic structure, part of the pattern. As you rest here, think about those voids. Bubbles of emptiness scattered through space, sitting quietly in the dark. Not doing much, not making noise. Just existing vast and hollow, waiting for light to pass through them. The universe carves spaces for nothing, and those spaces, strange as they are, help define the shape of everything else. Without voids, there would be no walls. Without emptiness, fullness would have no meaning. Absence creates context. Nothing makes something visible. And while voids show us what the universe looks like without matter, there are stranger configurations still. Places where stars exist inside other stars, where the rules of stellar physics bend into shapes we barely predicted, where death refuses to be final and objects we thought couldn't form turn out to exist anyway, glowing quietly in the cosmic dark. That's the territory we're entering next, into stars that shouldn't shine into objects born from collisions we thought impossible, into the strange defiance of stellar death. Imagine a Russian nesting doll made of stars, a neutron star dense as a mountain, compressed into a sphere 12 miles wide, hidden inside the bloated envelope of a red supergiant hundreds of times larger than our sun. One star wearing another star as a disguise. An object so strange that physicists predicted it in theory, but doubted it could exist in reality. Until 2014, when astronomers found one. In the 1970s, physicist Kip Thorne and astronomer Anna Zhitkov proposed a theoretical object that seemed absurd, even by astrophysics standards. What if they asked a neutron star and a massive star were in a binary system orbiting each other? And what if over time they spiraled closer together until the neutron star didn't collide with its companion, but instead sank into it, burrowing through layers of stellar atmosphere until it settled at the core? You'd have a star within a star, a neutron star engine buried inside a red supergiant envelope. Thorne and Zhitkov worked out the mathematics and concluded yes, theoretically possible, but rare, vanishingly rare. Maybe only a handful exist in the entire galaxy. For decades it remained a curiosity, a footnote in textbooks, a what-if scenario that probably never happened. Then in 2014, astronomer Emily Levesque and her team were studying red supergiants in the Small Magellanic Cloud, a dwarf galaxy orbiting the Milky Way. They were measuring chemical compositions looking at which elements appeared in the star's spectra. One star, HV2112, showed something strange. Too much lithium. Too much molybdenum. Elements that shouldn't be abundant in a normal red supergiant, but would be if nuclear reactions were happening in unusual ways at the star's core. The signature match predictions for a Thorne-Zhitkov object, a star with a neutron star heart. They couldn't confirm it absolutely. The evidence is strong, but not definitive. HV 2112 might be a Thorne-Zhitkov object, or it might be something else equally strange. But the discovery opened a door. These objects might actually exist. Theory might be reality. Stars within stars. Corpses hidden inside living suns. Think about the physics happening inside a Thorne-Zhitkov object. The neutron star at the core is incredibly dense, incredibly hot, generating energy through processes that don't occur in normal stars. Material from the outer envelope falls onto the neutron star, heating up, undergoing nuclear reactions, producing exotic elements. The star glows not from fusion in its core, like normal stars, but from the neutron star engine buried inside. It looks like a red supergiant from the outside, but the mechanism powering it is entirely different. It's camouflage, stellar mimicry, a dead star pretending to be alive by wearing the skin of its victim. How does a neutron star end up inside another star? The scenario requires precision. Two massive stars in a binary system. One explodes as a supernova, leaving behind a neutron star. The other continues evolving, eventually becoming a red supergiant. As the supergiant expands, its outer layers reach toward the neutron star. Friction from passing through this material slows the neutron star down, causing it to spiral inward. Eventually, it sinks into the supergiant's core. The process takes millions of years. It requires the stars to be at the right distance, the right mass, the right evolutionary stage. Too close, and the neutron star tears the supergiant apart. Too far, and they never interact. But when conditions align, you get something that shouldn't exist. A hybrid object. Two deaths merged into one strange life. Scientists estimate there might be a few hundred Thorne-Zhitkov objects in the Milky Way. Maybe fewer, maybe more. They're hard to identify because they look almost identical to normal red supergiants. Only detailed spectroscopy reveals the unusual chemistry. We might be surrounded by them and not know it. Stars with secrets hidden at their cores. Now, let me tell you about a different kind of stellar strangeness, a death that refuses to finish. In 2012, astronomers observed a supernova designated SN 2012Z. Supernovae are stellar explosions, the violent deaths of massive stars, or the thermonuclear detonation of white dwarfs. Once a star explodes, it's gone, destroyed, dispersed into space, except SN2012Z didn't disappear. The explosion faded as expected. But then years later, astronomers pointed telescopes back at the location and found something still there. A faint star sitting exactly where the supernova had occurred. The star had survived its own death. This phenomenon is called a zombie star, and it's associated with a rare type of supernova called type IAX. These are weaker than normal supernovae, releasing less energy, ejecting less material. Instead of completely destroying the star, they blow off the outer layers but leave the core intact. The star explodes but survives, dies but continues glowing. Type SYAX. Supernovae are strange for another reason. They happen in binary systems where a white dwarf is siphoning material from a companion star. The white dwarf accumulates matter until it reaches a critical mass and undergoes a thermonuclear explosion. In a normal Type 1 supernova, the white dwarf is completely destroyed. Nothing remains. But in a Type 1AX event, something goes wrong. Or right depending on perspective. The explosion is incomplete, asymmetric, weak enough that the white dwarf's core survives. What's left is a zombie, a stellar remnant that experienced an explosion but didn't die. It sits there faint and damaged, slowly cooling, carrying the scars of its failed death. Astronomers have identified dozens of zombie stars now, each one a reminder that even stellar death isn't absolute. Even explosions can be survived. In 2019, a team of scientists published research on a star called LP 40 365. This white dwarf is moving through space at incredible speed, about 2 million miles per hour, fast enough to escape the galaxy eventually. But what makes LP 40 365 truly interesting is its composition. It's made almost entirely of unusual elements: sodium, aluminum, silicon, the byproducts of incomplete thermonuclear burning. Scientists believe LP 40 365 is a zombie star, the surviving core of a type IAC supernova. The explosion launched it into space at extreme velocity, but didn't destroy it. It's now racing through the galaxy, a fragment of a failed death carrying evidence of an explosion. It survived. Imagine being that star, torn from your companion, blasted by your own fusion reactions, hurled into the void at relativistic speeds, and somehow impossibly still existing, still glowing faintly, still following the laws of physics, even though you've been through an experience that should have erased you. There's something poetic about survival against impossible odds, even for a star. Another strange stellar phenomenon involves white dwarf mergers. When two white dwarfs orbit each other, they emit gravitational waves, losing energy, spiraling closer together. Eventually, they collide. What happens next depends on the combined mass. If it's below a certain threshold, they merge into a single larger white dwarf. If it's above that threshold, the merged object becomes unstable and explodes as a supernova. But there's a narrow range where something stranger happens. The merger creates an object massive enough to reignite nuclear fusion, but not massive enough to explode immediately. The result is a star that shouldn't exist, a massive white dwarf burning helium at its core, temporarily brought back from stellar death. These objects are rare and short-lived. They burn for a few million years before exhausting their fuel and cooling into a stable white dwarf again. But for that brief window, they're alive, reanimated, zombies in the truest sense. The universe wastes nothing. Even stellar corpses get recycled. Here's a thought that might settle into your mind as you drift. Stellar death isn't simple. We teach it as a straightforward process. Stars burn fuel, run out, collapse, or explode, leave behind remnants. Clean categories, clear outcomes. But reality is messier. Stars can survive explosions. Remnants can merge. Dead cores can reignite. Objects we predict theoretically turn out to exist in nature, hidden in plain sight, waiting for the right observation to reveal them. Death in the cosmos is negotiable. In 2017, astronomers detected gravitational waves from colliding neutron stars. Two dead stellar cores spiraling together, merging in a cataclysmic event that released more energy in a fraction of a second than the sun will emit in its entire lifetime. But what interested scientists most was what happened after. Telescopes across the world turned toward the merger location and detected light. Not just the flash of collision, but a sustained glow lasting weeks. The merging neutron stars had created something new, either a more massive neutron star or possibly a black hole surrounded by a disk of superheated material radiating energy across the electromagnetic spectrum. And in that disk, in the extreme conditions of the merger, heavy elements formed: gold, platinum, uranium. Elements that can only be created in the intense neutron-rich environment of colliding stellar corpses. You're wearing stardust, the saying goes. But more specifically, if you're wearing gold, you're wearing the remnants of dead stars that collided billions of years ago. The ring on your finger, the atoms in your phone, forged in stellar death and scattered into space. Collisions create, death makes, endings become beginnings. Thorne, Zhitkov. Objects and zombie stars remind us that categories are human inventions. We create labels alive and dead star and remnant because we need to organize our understanding. But the universe doesn't care about our categories. It produces objects that blur boundaries. stars that are simultaneously alive and dead, explosions that fail, mergers that create, objects that shouldn't exist according to our simplified models, but do exist because physics is richer than our abstractions. And that's exciting. Every time we discover something that doesn't fit, we're forced to expand our understanding, to refine our models, to accept that reality is more complex, more interesting, more strange than we anticipated. Scientists initially thought white dwarfs were the final state for stars like our sun. Stable, inert cooling, slowly over trillions of years. Simple. Then we discovered they could explode as supernovae if they accumulated enough mass. Less simple. Then we discovered they could survive those explosions, that they could merge with other white dwarfs and reignite, that they could be used as cosmic distance markers, standard candles revealing the expansion rate of the universe. Each discovery added layers, complexity replacing simplicity, but also truth replacing approximation. The universe is what it is regardless of how we describe it. Our job is to update our descriptions to match reality, not the other way around. In 2020, researchers published simulations of Thorne-Jitkov object evolution. They modeled what happens over time to a star with a neutron star core. The simulations showed something unexpected. The neutron star buried inside the supergiant envelope doesn't just sit there passively. It stirs the material around it, creating convection currents mixing the stellar interior in ways normal stars don't experience. This mixing brings material from deep within the star to the surface, changing the star's appearance, altering its spectrum. It might explain why HV2112 shows unusual abundances of certain elements. The neutron star heart changes the star's behavior, hidden influence, invisible control. It's like discovering someone has been pulling strings you didn't know existed. The puppet looks normal, acts almost normal, but there's something underneath directing its movements. Let me ask you this. What does it mean for a star to be alive? We use the word metaphorically, of course. Stars aren't living in the biological sense. They don't reproduce, don't evolve through natural selection, don't have consciousness. But they do undergo processes remarkably similar to life. They're born in collapsing clouds of gas. They grow by accumulating material. They mature spending most of their existence in a stable state, fusing hydrogen into helium. They age transitioning through different phases. They die sometimes violently, sometimes quietly. And as we've seen, sometimes they refuse to die. Sometimes they merge, creating new stars from old remnants. Sometimes they hide inside other stars, living parasitically. The metaphor is stronger than it first appears. Zombie stars raise an interesting question about stellar classification. If a star explodes but survives, is it still the same star? It has a different composition, different structure, different evolutionary path. But it occupies the same location, retains some of the same matter. Ship of Theseus Stellar Edition. If you replace all the pieces, is it still the original philosophy meets astrophysics? The answer probably depends on how you define identity, which is a question humans have struggled with for millennia. The universe doesn't care. The zombie star continues existing, regardless of what we call it. Here's something that will sound strange, but is perfectly true. Most of the universe's history is still ahead of it. The universe is currently 13.8 billion years old. Stars like our sun will continue forming for trillions of years. White dwarfs will cool for quadrillions of years. The stelliferous era, the age of stars, has barely begun, which means zombie stars, Thorne-Jitkov, objects, white dwarf mergers, all the strange stellar phenomena we've discovered will continue happening. The universe will keep producing objects that don't fit our categories, that blur the lines between life and death, that challenge our understanding. And long after humanity is gone, long after Earth is cold, these processes will continue. Stars will be born, live die, and sometimes refuse to die completely. The cosmic drama will unfold, whether anyone is watching or not. There's something comforting about that. The universe doesn't need an audience. It performs for itself. As you rest here in the quiet, think about HV 2112 glowing faintly in the small Magellanic Cloud, a red supergiant with a secret at its core. If you could somehow survive the radiation and heat and descend through layers of stellar atmosphere, you'd eventually reach something impossibly dense. A neutron star embedded in the heart of a giant, driving the fusion reactions that keep the outer envelope glowing. Two stars merged into one, death and life coexisting. And think about LP 40-365 racing through space at 2 million miles per hour, a survivor of an explosion that should have destroyed it, a fragment carrying evidence of incomplete death. These objects exist, not in theory, not in imagination, but out there in space following physical laws, glowing faintly, waiting for telescopes, sensitive enough to study them in detail. Strangeness is real. It's not metaphor, it's measurement. And while stars that survive their own deaths show us that endings can be negotiable, there are places in the universe where the rules become even stranger. Planets where weather means something entirely different. Worlds where it rains glass or iron or diamonds. Where atmospheric pressure crushes matter into forms we can barely replicate in laboratories. Where temperature and chemistry create conditions so alien that even thinking about them requires stretching our imagination. That's the territory opening up ahead, the exotic weather of worlds beyond Earth, where rain doesn't fall as water and storms don't look like anything we've ever seen. Picture rain falling upward, wind moving faster than sound, clouds made of molten rock droplets of liquid metal cascading through an atmosphere hot enough to vaporize steel. Weather so extreme, it turns the familiar concept of a storm into something unrecognizable. This isn't imagination. This is planetary science. In 2013, astronomers using the Hubble Space Telescope studied a planet called HD 189733b. It orbits a star 63 light-years from Earth, a distance close enough to observe in detail, but far enough that we'll never visit. What they discovered changed how we think about weather beyond our world. HD 189733b experiences wind, but not the kind of wind you feel on your face during a storm. Wind moving at 5,400 miles per hour. That's 7 times the speed of sound, faster than a bullet, faster than anything in Earth's atmosphere could survive. And it's not blowing air, it's blowing silicate particles, tiny fragments of glass suspended in the atmosphere, accelerated to hypersonic speeds, scouring the planet's surface like a cosmic sandblaster. The planet appears blue when observed through telescopes. Beautiful, almost Earth-like in color. But that blue doesn't come from water. It comes from silicate haze scattering light. The planet is wrapped in a veil of glass dust, and that dust is moving faster than anything alive could withstand. If you stood on HD 189733b, if you could somehow survive the heat and pressure and radiation, the wind wouldn't feel like wind. It would feel like being hit by thousands of tiny bullets every second, shards of glass moving at hypersonic velocities, tearing through anything they encounter. It's raining glass, sideways, at 7 times the speed of sound. Weather we tend to think is water-based. Rain is water, clouds are water vapor, storms are movements of moist air. That's our experience on Earth, so we assume it's universal. But weather is just the movement and transformation of whatever substances exist in an atmosphere. On Earth, that's primarily nitrogen, oxygen, and water vapor. On other planets, it's different materials following the same physical principles, but producing wildly different results. HD 189733b is what astronomers call a hot Jupiter, a gas giant planet orbiting very close to its star, completing a full orbit in just over 2 Earth days. The proximity to its star heats the planet to extreme temperatures around 1600 degrees Fahrenheit on the day side. At those temperatures, silicates don't remain solid. They vaporize into the atmosphere, condense into tiny particles, and get caught in the planet's extreme wind patterns. The result is glass rain, driven by winds fast enough to circle the planet in hours. The temperature difference between the day side and night side of HD 189733b drives these winds. The day side perpetually facing the star heats up. The night side perpetually facing away cools down. The temperature differential creates pressure gradients, and pressure gradients create wind. But the wind doesn't blow in simple patterns. Computer models suggest the atmosphere forms jet streams, rivers of fast-moving gas that circle the planet at the equator. Material gets swept up in these jets, accelerated to incredible speeds, and carried around the planet in a relentless circulation. The planet never experiences calm weather, never has a still day. The wind never stops, never slows, never rests. Now, let me tell you about rain made of something even stranger than glass. In 2017, scientists at the National Ignition Facility in California conducted an experiment. They wanted to understand what happens deep inside ice giant planets like Neptune and Uranus. These planets have layers, a thin atmosphere at the top, then a thick mantle of water, methane, and ammonia, ice is under extreme pressure, and finally a rocky core. The mantle isn't solid and isn't quite liquid. It's something in between, existing under pressures millions of times greater than Earth's atmosphere. The scientists use lasers to compress a sample of polystyrene to conditions similar to those inside Neptune, temperature around 5,000 degrees Fahrenheit, pressure around 1.5 million times Earth's atmospheric pressure, and they watched what happened through X-ray imaging. The carbon atoms in the polystyrene separated from the hydrogen atoms. The carbon atoms under that extreme pressure and temperature crystallized. They formed diamonds. Tiny diamonds raining through the compressed matter like hail in a thunderstorm. Inside Neptune and Uranus, it rains diamonds. Let that settle into your mind for a moment. Deep within those blue-green worlds, beneath layers of hydrogen and helium, beneath the visible atmosphere, there's a region where pressure and temperature are so extreme that carbon crystallizes out of methane and falls inward as diamond rain. Millions of tons of diamonds drifting slowly through dense, compressed ices, accumulating over billions of years. A treasure hoard beyond imagination, existing in conditions no human could ever survive to see. The diamonds don't fall quickly. The material they're falling through is incredibly dense, almost syrupy in consistency. So the diamonds drift slowly, pulled by gravity toward the planet's core. Some scientists suggest there might be a layer of liquid diamond ocean surrounding the core, or a shell of compressed diamond thousands of miles thick. We'll probably never know for certain. We can't send probes into Neptune's interior. The pressure would crush any instrument we could build. But the physics is sound. Diamond rain is real, happening right now on worlds in our own solar system. Isn't it strange how wealth is contextual? On Earth, diamonds are valuable, rare, treasured. On Neptune, they're weather, a natural consequence of chemistry and pressure falling endlessly through an ocean no one will ever see. Value depends on scarcity. Scarcity depends on location, and location in the universe changes everything. Let me tell you about another planet with impossible weather, WASP-76. B discovered in 2016 orbits a star about 640 light-years from Earth. Like HD 189733b, it's a hot Jupiter. But WASP-76b is even more extreme. The day side of WASP-76b reaches temperatures around 4,500 degrees Fahrenheit, hot enough to vaporize iron. And that's exactly what happens. Iron from rocks and dust vaporizes into the atmosphere, creating iron vapor clouds. Then the wind carries that vapor to the night side, where temperatures are cooler, still hot by Earth standards, around 2,700 degrees Fahrenheit, but cool enough for iron to condense. It rains liquid iron, droplets of molten metal falling through an atmosphere of vaporized rock and metal. driven by winds that redistribute heat from dayside to nightside. The planet experiences an endless cycle of vaporization and condensation, with iron playing the role water plays on Earth. Astronomers detected this by observing the planet's spectrum as it transits its star. When the night side rotates into view, they see absorption lines from neutral iron atoms. When the day side is visible, those lines disappear, replaced by ionized iron. The iron is cycling between states evaporating and condensing, creating weather patterns, unlike anything in our experience. Imagine standing at the terminator, the boundary between day and night, on WASP 76b. On one side, iron vapor shimmers in the heat. On the other side, iron rain falls in sheets glowing red hot as it descends through the thick atmosphere. You couldn't stand there, of course. The radiation would kill you, the heat would vaporize you, the pressure would crush you. But if you had the right protective equipment and enough distance, you'd witness weather that defies every intuitive understanding of how planets should behave. Rain isn't always gentle. Weather isn't always benign. Here's a thought that might help you drift into sleep or keep you gently awake. Earth's weather, for all its variety and power, is mild compared to what exists elsewhere. Our strongest hurricanes, our most violent tornadoes, our heaviest rainstorms are nothing compared to the atmospheric dynamics on hot Jupiters or ice giants. We evolved in a remarkably calm environment. Nitrogen and oxygen atmosphere, water-based precipitation, wind speeds rarely exceeding 200 miles per hour, temperatures ranging from about minus 130 to plus 130 degrees Fahrenheit. That's a tiny sliver of the conditions planets can experience. We're lucky. Or rather, we're here because the conditions are mild. If Earth had weather like HD 189733b life, as we know it couldn't exist. Habitability is partly about having boring weather. Weather predictable enough, gentle enough that complex chemistry can persist long enough to become biology. Let me tell you about Titan, Saturn's largest moon. It's the only moon in our solar system with a thick atmosphere, and it's the only place besides Earth where we've confirmed stable liquid exists on the surface. But the liquid isn't water. It's methane and ethane. Hydrocarbons, the same chemicals that make up natural gas on Earth, existing as liquids because Titan is so cold. The average surface temperature is minus 290 degrees Fahrenheit. Titan has lakes, rivers, seas, an entire hydrological cycle, but with methane instead of water. Clouds form from methane vapor, rain falls as liquid methane, it fills lakes and rivers, evaporates, and repeats. The Cassini spacecraft, during its mission to Saturn, observed rain clouds on Titan, seasonal storms that dump liquid methane onto the surface, creating flash floods that carve channels through ice bedrock. It's rain recognizable as rain, following the same atmospheric dynamics as rain on Earth. But step outside into a Titan rainstorm and you wouldn't get wet. You'd get coated in liquid hydrocarbons, cold, chemically reactive, nothing like water. Weather following familiar patterns but using different materials. The universe improvises. In 2005, the Huygens probe built by the European Space Agency detached from Cassini and descended through Titan's atmosphere. It took photographs, measured atmospheric composition, recorded data as it fell. The images showed something remarkable, a landscape that looked almost Earth-like. Hills, valleys, river channels, shorelines, all carved by liquid methane over billions of years. The probe landed on a surface of ice pebbles surrounded by methane fog under an orange sky thick with organic haze. It transmitted data for 90 minutes before its batteries died. Those 90 minutes gave us our only ground-level view of weather on another world. And the weather was quiet. No wind, no rain, just cold, still air and the faint sound of methane dripping from somewhere beyond the probe's instruments. Weather doesn't have to be violent to be alien. Venus, our neighbor planet, has weather too. But Venus is hell. The surface temperature is around 900 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure is 90 times greater than Earth's. The atmosphere is almost entirely carbon dioxide with clouds of sulfuric acid. Those clouds don't produce rain, not at the surface. The sulfuric acid evaporates long before reaching the ground, recycled back into the atmosphere by the intense heat. But in the upper atmosphere, around 30 miles above the surface, conditions are milder. Temperature around room temperature, pressure similar to Earth's. And there in that narrow habitable zone, floating above the hellscape below, some scientists believe microbial life might exist. Floating in the clouds, metabolizing sulfur compounds, reproducing in droplets of sulfuric acid. It sounds absurd, but it's not impossible. Life on Earth exists in sulfuric acid pools. Microbes metabolize sulfur. The chemistry works. The question is whether Venus's clouds contain the right combination of chemicals, the right stability, the right conditions for life to emerge and persist. We don't know. We haven't sampled the clouds directly. But the possibility exists, a reminder that habitability isn't just about surface conditions. Sometimes the right weather creates pockets of habitability in otherwise hostile environments. Here's something to think about as you rest. Every planet with an atmosphere has weather. Mercury, with almost no atmosphere, experiences temperature swings of 1,000 degrees between day and night, but no weather. Mars has dust storms that can envelop the entire planet, wind-driven movements of fine particles that last for months. Jupiter has the Great Red Spot, a storm larger than Earth that's been raging for at least 350 years. Saturn has hexagonal cloud patterns at its north pole, a geometric weather system we don't fully understand. Each planet unique, each atmosphere following physics but producing different results. Weather is universal, but the details are local. In 2019, astronomers discovered water vapor in the atmosphere of K2-18b, a planet about 110 light-years from Earth. It's larger than Earth, but smaller than Neptune, orbiting in its star's habitable zone, where temperatures could allow liquid water to exist. The discovery made headlines. Water vapor on a potentially habitable planet. But the excitement was tempered by reality. K2-18b probably has a thick hydrogen atmosphere, crushing surface pressure, and conditions unlike anything on Earth. Finding water vapor doesn't mean finding a second Earth. It means finding one chemical we recognize in an environment that's still deeply alien. Weather includes water, but that doesn't make it familiar. Scientists now use computer models to simulate weather on exoplanets. They input atmospheric composition, stellar radiation, planetary rotation, and let physics predict what happens. The models produce wild results. Planets with permanent storms at the poles, planets with supersonic jet streams, planets where the atmosphere circulates in vast loops, transferring heat from dayside to nightside in hours. And occasionally, the models predict something familiar, a planet with temperatures in the habitable range, an atmosphere with reasonable pressure, weather that includes liquid water clouds and rain. Those are the planets we're most interested in, not because they're common, but because they are the ones where life as we understand it might exist. Where weather creates conditions stable enough for chemistry to become complicated for molecules to organize, for biology to emerge. We haven't found one yet, not definitively, but we're looking. As you drift here in the quiet, think about those distant worlds, planets where glass rains sideways at hypersonic speeds, where diamonds fall through compressed ices, where iron condenses out of vaporized rock, where methane drizzles onto lakes of liquid hydrocarbons, weather in all its variations, chemistry playing out in atmospheric theaters across the galaxy, physics indifferent to whether its products are beautiful or terrifying, just following rules, creating patterns, sculpting planets through wind and rain and time, and somewhere maybe a planet with weather mild enough for life, clouds that drift, rain that falls gently, winds that carry seeds instead of glass, a world where weather nurtures instead of destroys. We don't know if such places exist, but the universe is large and chemistry is persistent. Somewhere in the vast dark conditions might align, weather might become gentle, and in that gentleness, something might grow. But even as we search for familiar patterns, the universe continues broadcasting signals we don't fully understand. Radio bursts that last milliseconds, but release more energy than the sun produces in days. Stars whose brightness fluctuates in ways that defy explanation. Messages maybe, or just noise. Mysteries arriving from across the cosmos, challenging us to decode them, to understand them, to decide whether they're nature's strange clockwork or something else entirely. That's the territory opening ahead. Signals we cannot yet explain, mysteries arriving in pulses and patterns, waiting for interpretation. Imagine receiving a message so bright it outshines an entire galaxy, but only for a few milliseconds. A flash of radio energy so intense, so concentrated, that detecting it feels like catching lightning in a bottle. And then silence. No follow-up, no explanation. Just a pulse from the cosmic dark, leaving more questions than answers. In 2007, astronomer Duncan Lorimer was analyzing archival data from the Parkes Radio Telescope in Australia. The data was 6 years old, collected in 2001, sitting in storage waiting for someone to examine it. Lorimer was looking for pulsars, those spinning neutron stars we talked about earlier, sources of regular radio pulses. Instead, he found something that didn't fit any pattern, a single burst of radio energy lasting just 5 milliseconds, bright enough to be visible from halfway across the universe. The signal had arrived once, never repeated, and then vanished as mysteriously as it appeared. He named it the Lorimer Burst. And for years, scientists debated whether it was real or just instrumental noise, a glitch in the telescope, interference from Earth-based sources. Then more bursts appeared, different telescopes, different locations in the sky, all sharing the same characteristics. Incredibly bright, incredibly brief, coming from cosmological distances. We now call them fast radio bursts, or FRBL, and we have no idea what causes most of them. Let me give you a sense of the energy involved. A typical FRB releases as much energy in a few milliseconds as the sun emits in an entire day. Some release even more. The brightest FRBs ever detected released energy equivalent to what the sun produces in several days, compressed into a radio pulse lasting less time than a heartbeat. That's not just bright, that's cataclysmic. Something out there is producing bursts of energy so extreme that they propagate across billions of light years and arrive at Earth still detectable above the cosmic background noise. What could do that? What process generates that much energy in such a short time? The answer is, we don't know. We have theories, dozens of them, but no consensus. Colliding neutron stars, magnetar flares, evaporating black holes. Each explanation has problems. Each raises new questions. The universe is speaking, but we haven't learned the language yet. In 2012, astronomers detected an FRB designated FRB 121102. It followed the usual pattern, bright, brief, distant. But then, in 2015, it did something unprecedented. It repeated. The same location in the sky produced another burst, then another, then dozens more over the following years. This wasn't a one-time event. This was a repeating source, something actively producing FRBs on an irregular schedule. Suddenly, theories changed. If FRBs could repeat, they couldn't be caused by destructive events like colliding neutron stars. Those are one-time catastrophes. Whatever produces FRB 12110-2 survives the process and does it again. Scientists traced the repeating burst to a dwarf galaxy about 3 billion light-years away. Not a particularly special galaxy. Small, faint, unremarkable except for the fact that something inside it is broadcasting the brightest radio pulses in the known universe. Inside that galaxy in a region, astronomers haven't been able to pinpoint exactly something is flashing. Irregularly, unpredictably, powerfully. And we don't know what it is. Here's what makes FRBs even stranger. When radio waves travel through space, they interact with free electrons in the intergalactic medium, the sparse gas between galaxies. This interaction causes dispersion. Different frequencies of radio waves travel at slightly different speeds, arriving at Earth at slightly different times. By measuring the dispersion, astronomers can estimate how far the radio waves traveled. And for FRBS, the dispersion indicates cosmological distances. These signals cross billions of light years of space, passing through countless galaxies, clouds of gas, gravitational fields, and still arrive bright enough to detect. Whatever produces them must be extraordinarily powerful, and whatever they're made of must be able to survive the journey. The leading theory for repeating FRBs involves magnetars neutron stars with magnetic fields trillions of times stronger than Earth's. Under certain conditions, magnetars can experience starquakes, sudden fractures in their crust, that release enormous amounts of magnetic energy as radio waves. The theory explains the brightness, the brevity, the ability to repeat. Magnetars don't explode. They just crack, occasionally releasing bursts, then settling back into relative quiet. But not all FRBs repeat. Most appear once and never again, which suggests there might be multiple types of FRBs, different mechanisms producing similar signals, or one mechanism that sometimes repeats and sometimes doesn't, depending on conditions we haven't identified yet. The mystery persists. The signals continue arriving. And with each new detection, we refine our questions without necessarily getting closer to answers. In 2020, astronomers detected an FRB from within our own galaxy, the first time we'd observed one close enough to identify the source. It came from SGR 1935 plus 2154, a known magnetar about 30,000 light-years away. The burst wasn't as bright as extragalactic FRBS, but it had the same characteristics: brief, intense radio frequency. And it occurred simultaneously with an X-ray burst from the same magnetar, providing strong evidence that at least some FRBS come from magnetars. Problem solved. Not quite. The burst was weaker than typical extragalactic FRBs, which means either extragalactic FRBs are produced by more powerful magnetars, or there are additional mechanisms we haven't discovered yet. Science rarely provides clean answers. Usually it provides better questions. Now, let me tell you about a different kind of cosmic mystery, a star that dims in ways stars shouldn't. In 2015, citizen scientists analyzing data from the Kepler Space Telescope noticed something odd. A star designated KIC 8462852, located about 1,400 light-years from Earth, was dimming irregularly. Most stars, when they dim, do so in predictable patterns. Planets crossing in front of them create regular dips in brightness. Star spots cause gradual changes. Eclipsing binary companions produce periodic variations. KIC 8462852 didn't follow any pattern. It dimmed by different amounts at different times, sometimes by a few percent, sometimes by more than 20%, an enormous drop that couldn't be explained by planets or any natural stellar process. The star became known as Tabby's star, named after astronomer Tabitha Boyajian, who led the initial research, and it became one of the most studied stars in the sky because nobody could explain what was blocking its light. A planet couldn't block 22% of a star's light. Jupiter, the largest planet in our solar system, blocks only about 1% of the sun's light when it transits. To block 22%, you'd need something enormous. A swarm of planets, maybe, or something else. One hypothesis captured public imagination: a megastructure. An alien civilization building a Dyson swarm, a collection of solar panels or habitats orbiting the star to capture its energy. As they built, as the structure grew, it would block increasing amounts of starlight, creating irregular dimming patterns. The media loved it. Scientists were more skeptical. Extraordinary claims require extraordinary evidence. And while Tabby's star is strange, it's not necessarily artificial. But for a while, we didn't have a better explanation. The dimming was real. The irregularity was real. And nothing natural seemed to fit. Astronomers studied Tabby's star intensely. They observed it across multiple wavelengths looking for clues. They examined archival data going back over a century, searching for long-term trends. And they found something interesting. Historical photographic plates showed that Tabby's star had been gradually dimming over the past 100 years, losing about 16% of its brightness. That's unusual, but not unprecedented. Some stars do fade over time, but the irregular dramatic dips were newer. Something had changed about the star or its environment recently on astronomical timescales. One theory suggests dust. A massive cloud of dust perhaps from a destroyed comet or asteroid orbiting the star and occasionally passing in front of it. Dust would block light, and irregular clumps of dust would create irregular dimming, but dust should absorb more blue light than red light, creating a color change during dimming events. Initial observations didn't show the expected color shift, which cast doubt on the dust theory. Then more detailed observations did show color changes slight but measurable. The dimming events blocked more blue light than red light, consistent with dust. So, maybe dust is the answer. Maybe Tabby's star isn't alien technology, but just a star with unusually dusty surroundings, perhaps from a recent collision or breakup of objects in its system. But uncertainty remains. The dust theory explains most observations, but not all. The long-term dimming, the irregular dips, the specific patterns of brightness changes, all consistent with dust, but not definitively proven. Tabby's star remains strange, less mysterious than it was, but not fully explained. And that's often how cosmic mysteries work. We find something unexplained, we propose theories, we gather more data, and gradually the mystery becomes less mysterious. The possibilities narrow until we arrive at an explanation that fits most of the facts, but rarely all of them. There's usually a residual strangeness, a detail that doesn't quite fit a nagging sense that we're missing something. In 2019, astronomers discovered another star with irregular dimming patterns, VVV-WIT-0, 7 located in the constellation Sagittarius. It dimmed by about 80%, far more dramatically than Tabby's star, and stayed dim for several weeks before returning to normal brightness. 80%. Imagine the sun losing 80% of its light. The Earth would plunge into twilight. Temperatures would drop. Plants would struggle. Life would notice. What could block 80% of a star's light? The leading theory involves a massive disk of material, perhaps surrounding a planet or brown dwarf in a highly elliptical orbit. Once every few decades, the disk passes in front of the star, blocking most of its light temporarily. But we don't know. We're still gathering data, still watching, still waiting for the next dimming event to provide more clues. The universe contains more mysteries than answers, more questions than solutions. And that's not a failure of science. That's the nature of exploration. Here's a thought you can carry into the quiet. Signals arrive constantly. Light from distant stars, radio waves from galaxies, cosmic rays from supernovae, gravitational waves from colliding black holes. The universe is always broadcasting, always sending information across the void. Most of it passes through us unnoticed. We lack the senses to detect radio waves, to feel gravitational waves, to see beyond the narrow spectrum of visible light. But we've built instruments, telescopes, receivers, detectors, and they catch fragments of the cosmic broadcast, translate it into forms we can perceive, and present it for our interpretation. FRBS are part of that broadcast. Brief, intense, mysterious. Arriving from distant galaxies, carrying information about the universe at large scales, about extreme physics, about processes we haven't encountered in our local neighborhood. Each burst is a question, a cosmic riddle, and we're still learning how to answer. In 2021, scientists detected an FRB that repeated in a regular pattern. FRB 180916 produces bursts in a 16-day cycle. For 4 days, it's active producing multiple bursts. Then for 12 days, it's silent. Then the cycle repeats. Regular patterns suggest regular causes. Something about the source's environment or behavior follows a 16-day rhythm. Maybe it's orbiting something. Maybe it's precessing rotating in a way that only beams radio waves toward Earth during part of its cycle. The pattern is a clue. But like most clues in astronomy, it raises as many questions as it answers. What kind of object has a 16-day period? What mechanism could produce such regularity? We don't know yet. But the fact that we're asking more specific questions means we're making progress. Slowly, incrementally, the way science usually works. Some scientists have proposed that advanced civilizations could use FRBs as beacons, powerful radio pulses designed to be detectable across cosmological distances, announcing their presence to anyone listening. It's an interesting idea, but unlikely. FRBs require enormous energy, far more than any civilization would need for communication. And they're brief, unpredictable, carrying no obvious information content. If aliens wanted to send messages, there are more efficient methods. FRBs seem too wasteful, too random, but we can't rule it out completely. Maybe efficiency isn't the point. Maybe the energy expenditure itself is the message, a demonstration of capability. Or maybe we're misinterpreting natural phenomena as potential signals, because we're biased towards seeing patterns, toward imagining intelligence in the cosmos. Probably FRBs are natural. Extreme physics playing out in distant galaxies. Magnetars cracking. Neutron stars colliding. Black holes accreting matter. Processes we understand in principle but haven't observed directly at the required scales. But maybe not. Maybe some FRBs are different. Maybe in the vast catalog of detected bursts, a few carry information. Patterns hidden in the chaos. We'll only know if we keep listening, keep watching, keep analyzing. As you rest here in the quiet, think about those signals crossing the universe. Radio waves traveling for billions of years, passing through the space between galaxies, arriving at Earth as faint whispers of distant events. Most go undetected. They arrive when no telescope is pointing in the right direction, or they're too faint to register above noise, or they fall outside the frequency ranges we're monitoring, but some get caught, recorded, studied, and each one teaches us something, even if it's just that we have more to learn. Strangeness is constant, mystery is abundant. And the universe continues broadcasting, whether we're listening or not. But signals and mysteries aren't confined to distant galaxies or individual stars. Sometimes strangeness appears in the large-scale structures themselves, in the way galaxies interact, in the collisions that span millions of years and reshape cosmic neighborhoods. When galaxies meet, when they merge and tear and rebuild, they create forms that seem almost intentional, patterns that look like art, but emerge from nothing more than gravity and time. That's the spectacle unfolding next. The slow-motion dance of galaxies colliding, creating shapes we never expected, structures that challenge our understanding of how cosmic architecture works. Imagine two spiral galaxies each, containing hundreds of billions of stars, drifting through space for billions of years, and then slowly, inevitably meeting, not in a sudden crash, but in a gravitational embrace that lasts 100 million years. Stars don't collide. The distances between them are too vast, but the galaxies deform, tear each other apart with tidal forces creating shapes that look less like astronomy and more like cosmic calligraphy. Around 65 million years ago, about the time dinosaurs were going extinct on Earth, two galaxies in the constellation Corvus began their collision. We call them the antennae galaxies, now named for the two long streamers of stars and gas that arc away from the merger like insect antennae reaching into space. Those streamers are hundreds of thousands of light years long. tidal tails pulled from the galaxies by gravitational forces during the collision. Stars that once orbited peacefully in spiral arms now flung outward following trajectories that will never bring them back. The collision is still ongoing. The galaxies haven't finished merging. They're in the middle act of a process that will take another few 100 million years to complete. By the time they're done, both spiral structures will be destroyed, replaced by a single elliptical galaxy, a smooth blob of stars with no remaining memory of the elegant spirals that once existed. But for now, frozen in this moment of cosmic time, they're beautiful, strange. A collision measured not in seconds, but in epochs. Think about the time scale. 65 million years ago, the galaxies first touched. Gravitational interactions began pulling stars and gas into new orbits. Shock waves from colliding gas clouds triggered bursts of star formation. Massive stars formed, lived, and exploded as supernovae, all within the time frame of this single collision. And the collision is still happening, still unfolding, will continue unfolding for millions of years more. Human lifetimes are irrelevant on this scale. Civilizations rise and fall faster than galaxies can blink. When galaxies collide, stars don't hit each other. The distances between stars are enormous compared to their sizes. Even in a dense galaxy, the space between stars is vast emptiness. So, when two galaxies pass through each other, most stars sail through unimpeded, their paths altered by gravity, but not by physical collision. But gas clouds do collide. Gas fills the space between stars. And unlike stars, gas is diffuse enough that clouds from different galaxies can meet, compress shock, and heat. Those compressions trigger star formation. Suddenly, regions that were stable for billions of years become chaotic. Gas collapses, new stars ignite. Massive stars form in clusters, lighting up the collision zone with ultraviolet radiation. In the antennae galaxies, astronomers have identified over 1,000 regions of intense star formation. Stellar nurseries born from collision, places where stars are forming at rates hundreds of times faster than in the Milky Way. Creation through destruction. Order emerging from chaos. The Hubble Space Telescope has captured images of the antennae galaxies in extraordinary detail. You can see individual star clusters, bright knots of newborn stars glowing blue and white, dust lanes where gas is still collapsing, and threading through everything the tidal streamers, those long arcs of stars pulled from their original homes. The images are stunning. They look painted, deliberate, but they're just gravity playing out over timescales so long that the results appear frozen static, even though everything is moving, changing, evolving. Collisions like this will happen to our own galaxy. In about 4.5 billion years, the Milky Way and the Andromeda galaxy will collide. We're currently approaching each other at about 70 miles per second, closing a gap of 2.5 million light years. The math is straightforward. In roughly 4 to 5 billion years, first contact. The galaxies will pass through each other, swing back due to gravity, and collide again. Multiple passages each one further disrupting the spiral structures until eventually they merge into a single elliptical galaxy. Astronomers have already named the result Milkomeda, a blend of Milky Way and Andromeda, a galaxy that doesn't exist yet, but will given enough time. By then, the sun will be nearing the end of its life, expanding into a red giant, possibly engulfing Earth. But even if Earth survives, the night sky will be unrecognizable. The Milky Way's familiar band of light will be gone, replaced by a diffuse glow as stars scatter into new orbits. And Andromeda, currently a faint smudge visible to the naked eye, will dominate the sky, growing larger over millions of years, filling more and more of the celestial sphere until the collision is undeniable even to observers without telescopes. Imagine watching that if you could. Imagine seeing another galaxy approach over lifetimes, generations, millennia, the sky changing, new constellations forming, old ones dissolving, the Milky Way stretching, deforming, merging with the intruder. It would be beautiful and terrifying, a cosmic event on a scale that makes human concerns seem infinitesimally small. Now, let me tell you about a different kind of galactic collision, one that happened head-on. The Cartwheel Galaxy, located about 500 million light-years from Earth, looks exactly like its name suggests. A bright ring of stars and gas, perfectly circular, surrounding a dimmer central region. Spokes of material connecting the ring to the center like the spokes of a wheel. It's not a natural structure. Spiral galaxies don't look like this. Elliptical galaxies don't look like this. The cartwheel is the result of a smaller galaxy plunging directly through the center of a larger spiral galaxy, roughly 200 million years ago. The collision sent a shock wave rippling outward through the larger galaxy's disk, like a stone dropped into water. That shock wave compressed gas-triggered star formation and created the bright ring we see today. The ring is expanding, moving outward at about 200,000 miles per hour. It's currently about 150,000 light-years in diameter and still growing. Inside the ring, the original galaxy is trying to rebuild. Spiral arms are reforming, slowly pulled back together by gravity. But the ring dominates. It's the most prominent feature, the signature of a violent past. The smaller galaxy, the one that caused the collision, is still nearby. Astronomers have identified it, a small, irregular galaxy sitting just outside the cartwheel. It passed through, disrupted its victim, and now drifts in the aftermath, relatively unharmed. Collisions aren't always symmetrical. Sometimes one galaxy dominates. Sometimes both are destroyed. Sometimes, like in the cartwheel's case, one galaxy survives mostly intact, while the other is reshaped entirely. Outcomes depend on mass velocity angle of approach. Small changes in initial conditions produce wildly different results. There's a galaxy called Hoag's Object that looks even stranger than the cartwheel. Discovered in 1950 by astronomer Arthur Hoag, it consists of a bright central core surrounded by a perfect ring of blue stars. But unlike the cartwheel, there's almost nothing between the core and the ring, just darkness, empty space. The ring is separated from the core by a gap about 70,000 light-years wide. An impossible structure, or so it seemed when first discovered. How does a galaxy form a ring with a gap in the middle? The most widely accepted theory involves a collision similar to the cartwheel's. A smaller galaxy passed through the core, creating a shock wave that formed the ring. But in Hoag's object, the ring is older, more evolved, and the original disrupted material between the ring and core has dispersed or collapsed back inward. But this explanation has problems. The ring is too symmetrical, too stable. Computer simulations struggle to produce rings this perfect from collisions. Some astronomers have proposed alternative explanations. Maybe Hoag's object isn't a collision remnant, but a rare gravitational resonance, a configuration where orbits align in unusual ways. Or maybe it's the result of multiple collisions or a merger with a dark, matter-rich dwarf galaxy. We don't know. Hoag's object remains one of the most peculiar galaxies in the sky, a reminder that even our best theories sometimes fail to explain what we observe. And there's not just one Hoag's object. Astronomers have found a handful of similar ring galaxies, each one rare, each one strange, each one suggesting that the universe has more ways to arrange matter than our models predict. In 1877, astronomer Edouard Stephan discovered a compact group of galaxies in the constellation Pegasus. 5 galaxies clustered close together, clearly interacting gravitationally. Stephan's quintet, as it's now called, is one of the most studied galaxy groups in astronomy. 4 of the galaxies are actually close together, about 300 million light-years from Earth, locked in a gravitational dance. The 5th is a foreground galaxy much closer to Earth, appearing grouped with the others only by line-of-sight coincidence. But the 4 that are interacting are tearing each other apart. Tidal streamers connect them. Shock waves from colliding gas create visible filaments. Star formation bursts light up collision zones. And at the center, there's evidence of active galactic nuclei, supermassive black holes, accreting material stirred up by the interactions. It's chaos, beautiful, luminous, violent chaos. Four galaxies merging over hundreds of millions of years, creating a structure that will eventually become a single massive elliptical galaxy. Stefan's quintet gives us a laboratory for studying galactic interactions. Because multiple galaxies are involved, because they're at different stages of merging, we can see various phases of the collision process simultaneously. It's like watching a time lapse, but instead of speeding up time, we're observing many examples at once and assembling them into a sequence. Here's something to think about as you drift. Galaxies are not permanent. We see them as fixed objects, stable structures in the night sky. But they're dynamic. They grow by accreting gas. They merge with other galaxies. They're disrupted by close passes. They evolve over billions of years, changing shape, changing size, changing character. The Milky Way itself is a patchwork of smaller galaxies that merged over time. Astronomers have identified streams of stars, remnants of dwarf galaxies the Milky Way consumed billions of years ago. Those galaxies no longer exist as separate objects. They've been integrated, absorbed, their stars, now part of our galaxy. We live in a cannibal galaxy, a structure built from smaller victims. And that's normal. Most large galaxies grew this way. Mergers are common in cosmic history. In the early universe, when galaxies were closer together, collisions happened frequently. Now, as the universe expands, galaxies are more spread out, but mergers still occur. In dense galaxy clusters, where hundreds of galaxies orbit a common center, interactions are ongoing. Galaxies pass through each other, exchange stars, trigger bursts of star formation. The cluster itself is a slowly churning cauldron of galactic evolution. When galaxies collide, their supermassive black holes eventually merge too. This process takes time. The black holes start out at the centers of their respective galaxies. As the galaxies merge, the black holes spiral inward, sinking toward the center of the merged galaxy. Eventually, they form a binary, two black holes orbiting each other. They emit gravitational waves, losing energy, spiraling closer together. And finally, they merge in a cataclysmic event that sends ripples through space-time detectable across the universe. The LIGO and Virgo gravitational wave detectors have observed several black hole mergers, though mostly involving stellar mass black holes. Supermassive black hole mergers, the kind that happen when galaxies collide, are rarer and produce gravitational waves at lower frequencies. Future detectors like the space-based LISA mission, planned for the 2030s, will be sensitive to these lower frequencies. They'll hear supermassive black holes collide, events that mark the final stage of galaxy mergers. Collisions create. They trigger star formation, reshape, galaxies feed black holes. But they also destroy. Spiral structure painstakingly built over billions of years gets erased. Stars get flung into intergalactic space, exiled from their galaxies. Gas gets heated to temperatures that inhibit further star formation. The balance between creation and destruction defines galactic evolution. Collisions are transformative, but not always productive. Sometimes they just rearrange matter. Sometimes they quench star formation, turning vibrant galaxies into passive relics. As you rest here in the quiet, think about those galaxies. The antennae still merging, still pulling each other apart. The cartwheel expanding, rebuilding. Hoag's object, mysterious, perfect, inexplicable. Each one a monument to collision. Each one evidence that even on cosmic scales, nothing is permanent. Structures change, shapes evolve. What seems eternal is just slow. The universe builds and rebuilds, constantly, quietly, with patience measured in millions of years. And here's the thing. We're observing these collisions from a distance, seeing them frozen in time, because light takes millions of years to reach us. The antennae galaxies, as we see them now, completed their current configuration 65 million years ago. They've continued evolving since then, but we won't see those changes for another 65 million years. We're always looking into the past. Every observation is historical. Every photograph captures something that no longer exists in the form we're seeing. The galaxies have moved on. They're further along in their merger now. But their light hasn't caught up yet, so we see them as they were not as they are. Time and distance become tangled. Observation becomes archaeology. Astronomy becomes the study of ghosts. But even ghosts teach lessons. Even frozen moments reveal processes. And from these distant collisions, from these galactic wrecks scattered across the universe, we learn how matter organizes, how gravity sculpts, how time transforms. Collisions are common, mergers are inevitable, and through them, the universe creates structures grander than the pieces that came before. As we've drifted through bent light and pulsing stars, through voids and zombie suns, through exotic rains and mysterious signals, through galaxies tearing and rebuilding themselves, a pattern emerges. Strangeness isn't the exception. It's woven into the fabric of everything. The universe doesn't operate on human intuition, doesn't follow the rules we'd prefer. It follows its own logic, mathematical and indifferent producing phenomena that challenge our categories, blur our boundaries, defy our expectations. And in that defiance and that persistent strangeness, there's something worth carrying into sleep, a reminder that reality is richer, deeper, more textured than any single explanation can capture. That's where we're settling now, into the closing thoughts, into the gentle reminder that mystery isn't something to solve entirely, but something to rest within, to marvel at, to let drift through consciousness as the night deepens. We've walked through a universe stranger than dreams tonight, through light that bends around invisible mass, arriving at our eyes from paths it shouldn't take, through dead stars spinning faster than thought, keeping time more precisely than anything alive, through voids so empty they challenge the very idea of how matter should distribute itself across space. We've seen stars hiding inside other stars, wearing their victims like disguises. We've stood in the rain on worlds where glass falls sideways at hypersonic speeds, where diamonds drift through compressed oceans, where iron condenses from vaporized rock. We've listened to signals we cannot explain, flashes from the cosmic dark that outshine galaxies for milliseconds, and then vanish into silence. And we've watched galaxies collide in slow motion, tearing each other apart over 100 million years, creating shapes so beautiful they seem intentional, though they're just gravity and time, doing what gravity and time do. Each phenomenon strange in its own way. Each one real, measured, documented. Not science fiction, but science fact observations that forced us to expand our understanding, to accept that the universe is wilder, more inventive, more persistently surprising than we anticipated. Here's what strikes me most about these mysteries. They weren't found by looking for strangeness. They were found by looking carefully at ordinary things. Starlight, radio signals, galaxy distributions. Scientists pointed their instruments at the sky, expecting to confirm what they already knew, and instead discovered phenomena that didn't fit any existing framework. Gravitational lensing was predicted mathematically before it was observed, but Einstein himself doubted we'd ever see it. Too subtle, he thought. Too difficult to measure. And yet, Eddington measured it in 1919 during a solar eclipse, and now we use gravitational lenses routinely mapping dark matter, observing distant galaxies we couldn't otherwise see. Pulsars were discovered by accident. Jocelyn Bell was looking for quasars and found something that pulsed with such regularity, she half-jokingly wondered if it was aliens. It wasn't. It was something perhaps even stranger. A stellar corpse 12 miles across, spinning hundreds of times per second, more stable than any clock humanity had built. Fast radio bursts appeared in archival data signals, so brief and bright they seemed impossible. For years, scientists debated whether they were real or instrumental errors. Now we detect them regularly, and we still don't fully understand what causes them. Tabby's star dimmed in ways stars shouldn't. And for a moment, just a moment, we wondered if we were seeing evidence of alien megastructures. We probably weren't. It's probably dust. But the fact that we had to seriously consider the possibility that the observations were strange enough to warrant exotic explanations tells you something about how little we truly understand about stellar behavior. The universe keeps teaching, keeps revealing, keeps showing us that our categories are provisional, our explanations incomplete, our confidence often premature. And that's not frustrating, that's exciting, because it means there's always more to discover, always another layer beneath the surface, always a new question waiting behind every answer. Think about what we've learned just in the past few decades. Gravitational waves predicted in 1916, finally detected in 2015. 100 years between prediction and confirmation, and when confirmation came, it opened an entirely new way of observing the universe. We can now listen to space-time itself, rippling, hear black holes collide, detect events that produce no light, but shake the very fabric of reality. Exoplanets, the first one confirmed in 1995. Before that, we knew planets existed around our sun, but we didn't know if other stars had planets. Now we've discovered over 5,000 exoplanets, and we know that planetary systems are common. Almost every star has planets. The galaxy is full of worlds, most of them, nothing like Earth, most of them strange beyond our everyday experience. Dark energy discovered in 1998, when astronomers measured distant supernovae and found the universe's expansion is accelerating. Something is pushing galaxies apart, something that makes up about 70% of the universe's total energy, and we don't know what it is. We've named it, but naming isn't understanding. The more we learn, the more we realize how much we don't know. The sphere of knowledge expands, but so does the surface area of that sphere, the boundary where knowledge meets mystery. Every answer reveals new questions, and maybe that's how it should be. But maybe the point isn't to solve the universe, to reduce it to a set of equations we fully understand. Maybe the point is to engage with it, to marvel at it, to let it surprise us. Carl Sagan once said that we are a way for the cosmos to know itself. We're made of star material atoms forged in stellar cores, scattered by supernovae, gathered into planets, organized into life, into consciousness. And now, we're looking back at the stars, studying them, trying to understand where we came from. There's something poetic about that. The universe examining itself through us. Matter become aware, turning its attention outward and inward, simultaneously asking questions about its own nature. Do you ever wonder why we care about these things? Why we build telescopes, launch satellites, spend billions of dollars to observe distant galaxies that will never affect our daily lives? Maybe it's because curiosity is fundamental to being human. We're pattern seekers, question askers, explorers by nature. We see light from a distant star and we wonder what kind of star is it? How far away what's happening there? Or maybe it's because understanding the universe helps us understand ourselves. We're not separate from the cosmos. We're part of it. Learning how stars form, how galaxies evolve, how matter organizes, tells us something about the processes that led to us. Or maybe it's simpler. Maybe we look up at the night sky and feel wonder, and that feeling is enough. It doesn't need justification. It doesn't need to be useful. Wonder is its own reward. Tonight we've explored some of the strangest phenomena the universe offers. Light bending through curved space-time. Stars pulsing with neutron heart precision. Voids that shouldn't exist. Zombie stars surviving their own deaths. Glass rain and diamond oceans. Signals we can't explain. Galaxies tearing each other apart in gravitational embraces. Each phenomenon a reminder that reality is not constrained by human intuition. The universe doesn't care what we think is possible. It just unfolds according to physical laws, producing results that range from elegant to bizarre. And we get to observe it. We get to be here, conscious aware, able to point instruments at the sky, and capture photons that have traveled for millions or billions of years to reach us. We get to decode those photons, extract information, build models, make predictions, test them, refine them. We get to participate in the cosmic conversation, even if we're mostly listening, even if we understand only fragments. As you rest here, let these thoughts drift through your mind. Somewhere right now, light is bending around a massive galaxy, creating multiple images of a distant quasar. Somewhere, a pulsar is spinning, emitting pulses with clockwork precision. Somewhere in a void larger than we can easily imagine, there's almost nothing, just darkness and the slow expansion of space. Somewhere, a star is hiding inside another star, driving fusion reactions from within. Somewhere, it's raining glass or diamonds or molten iron. Somewhere, a fast radio burst is flashing, releasing energy equivalent to what the sun produces in days compressed into milliseconds. Somewhere, galaxies are colliding, their shapes deforming their stars, flung into new orbits, their futures rewritten by gravitational forces playing out over epochs. All of this is happening, right now, constantly. The universe is endlessly active, endlessly creative, endlessly strange. And we get to know about it. We get to study it, measure it, wonder about it. We get to be the conscious observers in a cosmos that doesn't require observation, but is richer somehow because we're here to witness it. Strangeness we've seen tonight isn't rare. It's fundamental. It's woven into the structure of reality at every scale, from the quantum foam at the smallest distances to the cosmic web at the largest. The universe refuses to be simple. But strangeness isn't randomness. Everything we've discussed follows laws. Physical laws, mathematical laws, laws that are discoverable, testable, predictable. The universe is strange, but it's not arbitrary. It follows rules even if those rules produce results that seem impossible. Light bends because mass curves space-time, and Einstein gave us the equations to calculate exactly how much bending occurs. Pulsars spin because angular momentum is conserved when stars collapse, and we can predict rotation rates from stellar mass and radius. FRBS follow dispersion relations that tell us how far they've traveled. Galaxies collide according to gravitational dynamics we can simulate on computers. Strangeness is lawful, mystery is structured, and that's what makes science possible. If the universe were truly random, truly unpredictable, we couldn't study it. But it's not. It's consistent. It follows patterns. And those patterns, once discovered, allow us to understand phenomena we never directly experience. You'll never stand on HD 189733b and feel glass rain at hypersonic speeds. You'll never visit the Bode's void and experience that profound emptiness. You'll never watch the antennae galaxies collide up close. But you can understand these things. You can know they exist. You can appreciate their strangeness from a distance. Knowledge bridges the gap between here and there, between now and then, between the familiar and the impossible. I want to thank you for drifting with me tonight through these cosmic mysteries, for staying curious, for being willing to explore phenomena that don't fit neatly into everyday experience, for letting strangeness become familiar, one whisper at a time. The universe is large, larger than we can fully comprehend. And within that largeness, there's room for phenomena we haven't discovered yet, objects we haven't imagined, processes we haven't predicted. The mysteries we've explored tonight are just a small sample of what's out there waiting for the right telescope, the right instrument, the right observer to reveal them. Science is an ongoing conversation between humans and the cosmos. We ask questions through our observations. The universe answers through its behavior. And slowly, incrementally, conversation by conversation, we build understanding. But understanding doesn't eliminate wonder. If anything, it deepens it. The more we learn about gravitational lensing, the more remarkable it becomes that light can navigate curved space-time so precisely. The more we learn about pulsars, the more astonishing it is that dead stars can keep such perfect time. The more we learn about galaxy collisions, the more beautiful those tidal streamers appear, knowing they're made of billions of individual stars following gravitational trajectories. Knowledge enhances appreciation. It doesn't diminish it. So, As you drift into sleep tonight, carry these images with you: light bending, stars pulsing, voids stretching, galaxies dancing, rain falling in forms you've never experienced, signals flashing from across the universe. Let them blend into your dreams, these strange truths. Let them remind you that reality is richer than fiction, that the universe is more inventive than any story we could write. And when you wake, the strangeness will still be there. Light still bending, stars still pulsing, mysteries still waiting. The universe doesn't pause. It continues its slow, strange unfolding, whether we're watching or not. But we are watching. We're here, conscious, curious, capable of wonder. And that makes us part of the story. Not just observers, but participants, made of the same elements as stars, following the same physical laws, existing within the same strange cosmos. We belong here, in this universe of bent light and zombie stars, of diamond rain and colliding galaxies. We're not separate from the strangeness. We're made of it. Sleep well, friend. Dream gently. And know that the universe in all its persistent strangeness continues spinning through the dark, creating wonders we've seen and wonders we haven't, mysteries solved and mysteries waiting. Thank you for listening. Thank you for wondering. Thank you for being here in this quiet moment, letting the cosmos reveal itself through whispers and mathematics, through observation and imagination. There are more stories waiting, more phenomena to explore, more mysteries to encounter. The universe is endlessly generous with its strangeness, and we've only begun to catalog it. So, rest now. Let these thoughts settle like cosmic dust. Let wonder become the last thing you feel before sleep. And when you're ready, when curiosity calls again, there will be new discoveries to share, new observations to ponder, new reminders that we live in a universe far stranger and more beautiful than common sense suggests. Until then, sleep well. Dream of light-bending stars, singing voids, holding secrets, and galaxies dancing through time. Good night,